The coral reef at midday is a marketplace in motion, a vast, sunlit network of buyers and sellers, hunters and scavengers, each operating within its own niche, yet all bound by the same invisible economy of energy. Shafts of light fall through the shallow water, glinting off scales, fins, and coral heads. Tiny damselfish graze on algae pastures. Cleaner wrasses advertise their services like meticulous artisans. Parrotfish grind coral into sand, reshaping the landscape grain by grain. And moving deliberately through this living city, thick-bodied and heavy-jawed, comes one of the reef's most powerful brokers, the grouper. The grouper is a predator of opportunity but not of waste. It is built like a living vault, large, muscular, with a mouth so wide it can engulf prey whole, yet capable of remarkable finesse. Its hunting strategy, unlike the raw speed of barracuda or the persistent pursuit of reef sharks, relies on control and coordination. It is a master of leverage, an animal that has learned through evolution and experience that working with others often pays higher dividends than hunting alone. The camera follows one as it glides between coral spires, its thick fins fanning the water with slow, powerful strokes. It pauses above a maze of rock and branching coral, where a school of small reef fish scatter at its shadow. Then, it does something unexpected. The grouper hovers still, lowers its head slightly, and performs a rhythmic shake, a deliberate, coded gesture. Within seconds, a sinuous figure emerges from a nearby crevice. A moray eel, long and flexible, rises from the darkness like a ribbon of muscle. This is no confrontation. It is an invitation, and the beginning of a joint venture. In the complex economy of the reef, the grouper and the moray eel are unlikely business partners. One dominates open water, the other commands the labyrinthine interior of coral. Each has limitations that the other offsets. Prey fish, seeking refuge, dart between the two realms, the open and the enclosed, as if navigating a border economy. Alone, the grouper can corner but not chase them into crevices. Alone, the moray can flush but not capture those that escape into open space. Together, they close every escape route. Their partnership represents a rare and sophisticated form of interspecies cooperation, one that operates through mutual benefit and clear communication. The grouper's recruitment signal, the head shake, is no random twitch. It's a learned behavioral code, repeated consistently across populations from the Red Sea to the Caribbean. The motion tells the moray, in effect, that a hunt is available and that the grouper is willing to share the profits. The moray responds by leaving its crevice, joining the grouper as they patrol the reef together, moving in complementary arcs. The grouper flushes schools of small fish toward the coral, driving them into the narrow crevices the eel knows so well. Then, with perfect timing, the moray lunges inside, twisting through the maze to chase the prey back into the grouper's waiting mouth. It is a remarkable demonstration of parallel specialization. The grouper's advantage lies in speed and pressure. Its sudden rushes through open terrain disrupt prey schools, forcing split-second decisions. The moray's advantage is reach and maneuverability, its ability to enter the coral maze and root out what cannot flee. Neither species dominates the other. Instead, they operate like co-managers of a shared enterprise. The profits are paid in calories, the reward of efficiency, a 50-50 distribution when both strike successfully, or patience when one must wait for the other to feed first. Unlike hierarchical predator systems, this partnership thrives on reciprocity rather than dominance. For decades, scientists underestimated the cognitive flexibility behind such behavior. Cooperative hunting requires not just physical adaptation, but communication, trust, and memory. A grouper must recognize a moray as an ally rather than a competitor, a decision that involves suppressing aggression in favor of strategy. It must also remember which individuals have proven effective collaborators and which have not. Research in the Red Sea has shown that groupers will actively seek out particular morays known to cooperate well, returning to them repeatedly for future hunts. This level of partner selection hints at a rudimentary form of social intelligence, the ability to evaluate reliability and form long-term working relationships across species lines. As the camera follows their patrol, the dynamic between them becomes clear. The grouper leads, scanning the terrain ahead, its eyes tuned to movement. The moray trails close behind, weaving in and out of holes like a shadow. Occasionally, the grouper hovers again and performs another headshake, signaling a new target zone. This gesture may seem simple, but it represents a cross-species vocabulary, an interface of body language that has evolved not through shared ancestry, but through shared necessity. The moray, attuned to the pattern, accelerates, slipping into the coral with precision. A cloud of small fish bursts from the crevice, panic scattering them into open water. The grouper surges forward, mouth opening wide, creating a vacuum that sucks in two fish at once. The moray emerges moments later, jaws full. Both return to slow, synchronized movement, partners satisfied with the shared outcome. This pattern of coordinated foraging extends beyond a single hunting session. Groupers, particularly large individuals, maintain patrol routes across their territories, revisiting productive hunting zones with clockwork precision. These routes can span tens of meters, forming invisible circuits through the reef's mosaic of coral heads and sand patches. In economic terms, each patch is a market, a site where prey density fluctuates, where risk and reward must be recalculated daily. The grouper's success depends on knowing when and where to invest its effort, optimizing the return from each patrol. If prey populations drop in one area, it shifts to another, often recruiting different moray partners depending on local availability. These are not random wanderings, but structured supply chains in a dynamic marketplace of food and opportunity. The relationship extends to other species as well. In some regions, groupers have been observed signaling not just to morays, but to octopuses and even Napoleon wrasses, adapting their cooperative strategies to their specific strengths of each partner. The octopus, like the eel, can flush prey from tight spaces, but its behavior is more independent and less predictable, a less reliable subcontractor, as it were. The wrasser, meanwhile, specializes in prying open shells and rocks, expanding the partnership's range of potential prey. Each collaboration demonstrates the grouper's behavioral flexibility, its ability to tailor cooperation based on context. Evolution has made it both a predator and a negotiator, a creature that maximizes efficiency not through strength alone, but through intelligence applied to opportunity. The camera lingers now on the grouper's massive head, its eyes scanning the reef as cleaner wrasses approach. Like the moray, the grouper depends on maintenance partners to keep its operation running smoothly. The small wrasses dance in front of its mouth and gills, removing parasites, dead tissue and debris. The grouper tolerates the intrusion, remaining still as the cleaners work. These interactions are another form of exchange, a service contract that sustains the health of both parties. The wrasses gain food and protection, while the grouper gains hygiene and longevity. The reef's economy runs on such transactions, a continuous cycle of risk and reward, debt and repayment, all governed by natural selection rather than conscious design. Groupers are not territorial in the way morays are, yet they maintain zones of familiarity. Hunting grounds they patrol regularly, often returning to the same coral formations year after year. Large individuals dominate these routes, using size and experience to secure the most productive areas. Smaller groupers linger on the margins, waiting for openings, sometimes forming temporary alliances to share access to richer feeding grounds. Within this network, competition and cooperation coexist, mirroring the balance that underlies the reef itself. Each predator must constantly weigh aggression against opportunity, short-term gain against long-term survival. At dusk, as the light fades and the reef softens into shades of indigo and bronze, the grouper's patrol slows. The moray retreats to its den, slipping into the dark corridors it calls home. The grouper remains outside, resting above the coral, gill covers pulsing rhythmically. The day's transactions are complete. Yet even in stillness, the system continues. Prey fish reorganize, cleaners return to their stations, and the coral polyps extend their tentacles for the night's plankton bloom. The grouper, half hidden in shadow, is both participant and overseer in this economy of life. Its partnerships, its patrols, its willingness to collaborate, all reveal a truth that extends beyond its species, that in nature, competition and cooperation are not opposites but currencies of the same market. The grouper survives by striking deals, alliances built on precision timing, mutual benefit, and the unspoken logic of evolution. In the ever-shifting coral metropolis, it is less a solitary hunter than a strategist, a reef negotiator whose success lies not in dominance, but in the art of the deal. In the sunlit shallows of the Indo-Pacific, where coral spires rise like the submerged ruins of an ancient city, a massive blue-green silhouette drifts with the confidence of an old empire. Its forehead bears a prominent hump, its lips are thick and expressive, and its scales shimmer with iridescent hues that shift with every turn of the light, sapphire, jade, and gold. This is the Napoleon fish, also known as the humphead wrasser, one of the largest reef fish on Earth and among the most intelligent. It is both engineer and enforcer, custodian and opportunist, a creature whose appetite quietly maintains the very structure of the coral realm it inhabits. The reef is a society of balance, but not a peaceful one. Every square inch of coral is contested ground. Algae seek to smother it, starfish to consume it, and countless invertebrates to bore into its skeleton. In this crowded world, where competition runs deep and unchecked growth can destroy the whole, the Napoleon fish plays a crucial stabilizing role, a biological regulator that keeps the reef's infrastructure intact. Its presence ensures that no single species of prey dominates. Its diet, diverse and deliberate, targets some of the most destructive creatures in the ecosystem, including the venomous crown-of-thorns starfish, a predator that can devastate entire coral colonies if left unchecked. The camera moves closer to reveal the mechanics of the hunt. The Napoleon fish hovers over a coral ledge, watching a starfish crawl sluggishly across the substrate. Its small eyes, rimmed with gold, scan the scene with quiet intelligence. Then, with a slow, deliberate motion, it tilts forward, extending its thick lips toward the spiny prey. There is no haste in the strike. This is a hunter that can afford patience. With a sudden suction force, the fish clamps down and flips the starfish upside down, an act that exposes its vulnerable underside. In the following moments, the fish delivers precise, crushing bites, each powered by powerful pharyngeal jaws hidden deep within its throat. Within minutes, the starfish's arms are reduced to fragments, and what could have been a coral-eating disaster becomes nutrition for the reef's silent guardian. Few animals exhibit such refined control over their environment. The Napoleon fish is one of the few fish species known to use tools, a behavior once thought exclusive to mammals and certain birds. When faced with prey encased in tough shells, such as clams or sea urchins, it gathers the hard-shelled object in its mouth and swims upward before releasing it onto a rock or coral anvil below. The sound echoes across the reef, a sharp crack of impact, followed by a second attempt if needed. Some individuals are even selective, preferring particular stones whose angles or textures yield the best results. These repeated behaviors suggest a degree of foresight, experimentation, and learning. What we are seeing is not instinct alone, but a process of problem-solving, evidence of a flexible intelligence adapted for survival in one of nature's most complex ecosystems. This intelligence is paired with patience, an attribute mirrored in the species' slow biological rhythm. The Napoleon fish grows at a glacial pace by reef standards. It takes nearly a decade to reach sexual maturity, and large adults can live for over half a century. Such longevity allows individuals to develop and refine their hunting techniques over time. It also grants them the ecological stability to become keystone species, organisms whose influence shapes entire communities. By preying on coral predators and maintaining a delicate equilibrium between grazers and reef builders, they ensure the coral's long-term survival. In the absence of these massive wrassers, crown-of-thorns starfish can reproduce unchecked, their larvae drifting like living shrapnel across the reef, stripping entire coral gardens bare within months. Thus, each bite of a Napoleon fish is more than a meal. It is maintenance, a daily act of ecological governance. Yet such a strategy comes with risk. Slow growth and late maturity make the species vulnerable to overfishing. A single lost individual represents years of ecological labor undone. Large Napoleon fish are rare precisely because their long-term investment strategy trading rapid reproduction for endurance, only works in stable environments. In a human-altered ocean, this once effective approach has become a gamble. Their populations have declined drastically in many regions due to targeted fishing for their meat and ornamental value. The irony is striking. By removing the reef's protectors, humans destabilize the very ecosystems they depend on for biodiversity and fisheries. From an evolutionary perspective, the Napoleon fish's entire life is structured around flexibility and adaptation. Its reproductive system is a masterpiece of efficiency in low-density populations. Like many wrasses, this species is protogynous, meaning individuals begin life as females and can later change sex to become males. This ability allows populations to adjust their reproductive structure dynamically. When dominant males die or disappear, the largest females undergo a physiological transformation, converting their ovaries into testes, changing behavior, and even altering coloration and body morphology. Within weeks, the new male assumes control of a territory and mates with a harem of females, ensuring that no reproductive opportunities are wasted. It is, in essence, nature's form of corporate restructuring, a flexible hierarchy that maximizes efficiency in an unpredictable environment. The transformation process itself is one of biology's most fascinating hormonal feats. The shift is triggered by social cues, the absence of a dominant male or changes in population density. Hormonal cascades alter gene expression, gradually restructuring the gonads and modifying physical appearance. Females grow larger, their coloration deepens, and their behavior shifts from cooperative to territorial. In small, isolated reef systems where competition is low and mates are scarce, this system ensures continuity. Rather than rely on random luck to maintain gender ratios, the species has engineered its own internal market correction. The result is a population that remains resilient even under fluctuating conditions, provided that enough individuals live long enough to reach maturity in the first place. The daily rhythm of a Napoleon fish's life mirrors its long-term evolutionary strategy. It is not a fast or impulsive animal. It patrols the reef with measured calm, covering the same routes over and over, as if inspecting the health of its dominion. Each coral head, each sandy patch, is part of a network it knows intimately. The fish's large, thick lips probe into cracks where crustaceans hide, while its pectoral fins fan the sand to expose buried prey. Between meals, it often visits cleaning stations, where small wrasses and gobies remove parasites and dead skin. These interactions are crucial. For a species that can live half a century, maintenance is not optional but essential. Cleaner fish play the role of health technicians, extending the Napoleon fish's lifespan and ensuring it remains fit enough to continue its ecological duties. The large wrasse tolerates these smaller creatures crawling into its gills and mouth, a delicate trust agreement sustained by millennia of coevolution. As the sun shifts and the reef brightens, the Napoleon fish becomes a moving focal point for activity. Smaller fish track its passage, scavenging leftovers or using its bulk as temporary shelter. Even predators like reef sharks ignore it, deterred by its sheer size and thick mucus-covered scales that make it difficult to grasp. Despite its power, the Napoleon fish is not a reckless killer. It hunts selectively, choosing targets that pose the greatest benefit to the reef's stability. The removal of coral predators, the crushing of invasive starfish, the turnover of sand through its foraging, all these acts contribute to a balanced system. It is, in many ways, the reef's unsung manager, enforcing order not through dominance but through consistency. As the day wanes, the Napoleon fish slows its patrol and drifts toward the deeper slope of the reef. It finds a sheltered ledge, lowers its massive body, and rests, entering a state of semi-alert stillness. Its thick eyelids, a rarity among fish, close partially, shielding its sensitive eyes from nocturnal plankton that glow faintly in the water column. The reef around it hums with transformation. Diurnal fish retreat to safety, and nocturnal hunters emerge. Crustaceans click in the dark, and the current carries the scent of change. The Napoleon fish remains still, its presence alone enough to deter intruders. It has no need to assert its power. Its existence, its longevity, and its role in maintaining balance speak for themselves. In the grand accounting of the reef's economy, the Napoleon fish is both investor and regulator. Its slow growth, intelligence, and capacity for adaptive transformation embody evolution's long-term strategy: stability through patience, intelligence through necessity, resilience through change. Where other species rise and fall in frantic cycles of reproduction and collapse, this ancient fish endures by thinking in decades, not days. It spends its life solving problems the reef cannot solve alone, controlling pests, managing space, and ensuring the infrastructure of coral civilization remains intact. As dawn returns the following morning, sunlight once again filters through the water, illuminating the sleeping giant as it stirs. It glides from its resting place, fins spreading wide like banners unfurled, and resumes its patrol. Around it, the reef awakens, cleaner fish darting, corals unfurling, schools of juveniles moving in tight formation. In the midst of this teeming complexity, the Napoleon fish remains the quiet constant, a deliberate, enduring presence in a world built on transience. It is not the fastest, nor the fiercest, nor the most prolific, but it is among the most important. The coral empire depends on it, as all societies depend on their unseen architects, those who keep the system stable, not for glory, but for survival itself. Beneath the surface of a shallow tropical reef, where sunlight filters through clear turquoise water and scatters in a dance of flickering gold, a shape glides with ghost-like grace across the sand. It changes color as it moves, from pale beige to the deep brown of coral rubble, and then vanishes altogether, becoming part of the seafloor. Only when it begins to stir again do we realize we are watching one of the most intelligent and industrious architects in the ocean, the octopus. To call the octopus a builder is no exaggeration. In an environment where shelter is currency and every square inch of hiding space can determine survival, the octopus has turned architecture into an evolutionary art form. It does not inherit burrows or coral crevices, it creates its own. With soft, boneless anatomy and a mind distributed across 8 independent limbs, it constructs complex shelters from whatever the sea provides: shells, stones, bottles, coconuts, even discarded trash. Each den is a project, a feat of design tailored to the local terrain, and everyone tells the story of a creature balancing risk and reward through planning, experimentation, and experience. The camera descends to follow an individual as it glides across the sandy plain of the reef. Its body pulses gently, changing texture to match the fine-grained sediment below. The octopus stops beside a small pile of broken shells, evidence of its recent meals. With deliberate precision, it begins to rearrange the fragments. 2 arms pull a scallop half into position, another arm adjusts a conch shell, while the remaining limbs sift sand to level the base. The octopus's arms do not merely obey orders from a central brain. Each contains its own mini-network of neurons, capable of making decisions independently. These branch offices handle much of the tactile and motor coordination, freeing the main brain to focus on strategy. What we see then is not random movement, but a sophisticated parallel operation, a multi-limbed workforce executing a blueprint conceived in real time. It takes hours, sometimes days, to build a perfect den. The octopus weighs its investments carefully. Every minute spent rearranging materials is a minute not spent hunting. Yet the payoff is substantial. A well-built den provides protection from predators such as moray eels, groupers, and sharks. It also serves as a staging ground for ambushes. When prey approaches, a crab, shrimp, or passing fish, the octopus can launch from its door with astonishing acceleration, enveloping its target in a cloak of arms before the victim realizes the danger. In this economy of energy and safety, the den is both home and hunting blind, a structure where architecture and predation merge. Some octopuses take construction even further, collecting portable armor. One of the most striking examples is the so-called coconut octopus, a species found on sandy seafloors in the Indo-Pacific. These animals scour their environment for discarded coconut halves or clamshells, carrying them across the seabed like nomadic builders transporting materials for amabile shelter. When danger looms, the octopus retreats inside, closing the shells tightly around its body. This behavior demonstrates foresight, a rare cognitive ability in the animal world. The octopus does not collect shells for immediate use. It anticipates future threats and prepares accordingly. Such actions suggest a capacity for delayed gratification, a hallmark of complex intelligence that rivals some vertebrates. The daily schedule of an octopus reflects the rhythms of both builder and opportunist. By day, it tends to its den, cleaning debris and rearranging protective barriers. Its eyes, capable of detecting polarization patterns in light, constantly scan the surroundings for movement or changes in shadow. By night, it becomes a hunter. Emerging under cover of darkness, it glides silently across the reef, its arms probing into crevices where crabs sleep and mollusks rest. It hunts not with brute force, but with strategy. Some arms explore, others coordinate, and still others act as sentinels, feeling the currents for the approach of predators. The entire body functions as a synchronized machine, guided by distributed intelligence. Each limb knows what the others are doing without conscious instruction, an evolved efficiency that allows the octopus to multitask with seamless precision. But in a reef full of opportunists, no investment goes uncontested. Fish and crustaceans are frequent trespassers, scavenging leftovers from an octopus's meals or stealing the very materials it uses to build. Small reef fish, such as wrasses and gobies, lurk near the entrance of dens, darting in to snatch scraps the moment the owner departs. Even larger competitors like eels occasionally attempt hostile takeovers, forcing the octopus to abandon its home. Some species respond with territorial innovation. They construct secondary dens nearby, branch offices, so to speak, where they can retreat if their primary residence is compromised. The octopus thus spreads its assets across multiple locations, an instinctive version of risk diversification. The more complex the predator landscape, the more distributed its shelter network becomes. Security maintenance is constant and costly. The octopus must regularly inspect and reinforce the entrance to its den, clearing sand displaced by currents and repairing damage caused by nocturnal intruders. Sometimes this vigilance extends to deception. Octopuses have been observed rearranging shells and coral fragments to disguise the entrance entirely, creating false walls or misleading piles of debris that blend seamlessly into the environment. These are not permanent fixtures, but tactical designs, camouflage for a house that may move tomorrow. To conserve energy, the octopus repurposes old materials whenever possible, reusing shells or stones that once belonged to other animals. Its construction habits mirror recycling economies. Every object retains value as long as it can serve a new purpose. Inside the den, the octopus keeps order with meticulous care. The interior remains clean. Debris is expelled through jets of water from its siphon, a system akin to a self-cleaning mechanism. Waste and leftover prey shells are piled outside, forming what biologists call a midden, a visible record of the animal's hunting success and occupancy duration. These piles can grow large enough to attract attention, drawing both potential mates and unwanted visitors. For predators, a midden signals opportunity. For other octopuses, it advertises real estate availability. The octopus, in turn, learns to balance visibility with concealment, a constant trade-off between attracting mates and inviting danger. One of the most remarkable aspects of octopus architecture is its adaptability to changing conditions. When storms or strong currents disrupt the seabed, the octopus reacts immediately, gathering scattered materials and rebuilding. This rapid reconstruction reveals a form of spatial memory and problem-solving unmatched among invertebrates. It recalls where objects were, how they fit, and how to reassemble them into a functional shelter. Studies show that octopuses can recognize individual objects and remember their positions for days, demonstrating a level of cognitive mapping more often associated with mammals or birds. Each den, then, is not just a structure. It is an external memory system, a physical manifestation of the octopus's mental model of its environment. Defense extends beyond walls. When flight or concealment fails, the octopus deploys its most famous weapon, ink. Released from a gland near the rectum, the ink cloud functions as a smokescreen insurance policy, a literal payout in the currency of confusion. It is not simply a dark dye. It contains compounds that irritate predators' senses and disrupt chemical tracking, masking the octopus's scent trail as it escapes. The animal often couples this with rapid color change and jet propulsion, shooting backward through the water while its pursuer flounders in the cloud. In terms of biological cost, ink release is expensive. The glands require significant energy to refill. But the benefit, survival, far outweighs the expense. Like all insurance, it is only valuable when catastrophe strikes. Perhaps the most striking parallel between octopus behavior and human enterprise lies in how it balances time. Every decision, whether to hunt, build, repair, or hide, involves trade-offs between immediate gain and long-term safety. Time spent perfecting a den reduces time available for foraging. Too much hunting exposes the octopus to predators. Too little maintenance risks collapse. Evolution has fine-tuned this equilibrium into instinctive project management. The animal continuously recalculates the most efficient allocation of its effort, guided by environmental feedback, prey abundance, water conditions, predator density. In this sense, the octopus behaves like a strategist, adjusting its workflow to match shifting market conditions in the reef economy. As the camera pans outward, we see the reef's broader architecture, a mosaic of coral towers, sponge gardens, and sandy expanses, each occupied by animals conducting their own forms of construction and trade. Among them, the octopus stands out not for its strength or permanence, but for its adaptability. Its homes may be temporary, its materials fragile, yet its intelligence ensures survival through design. When night falls again, the reef glows faintly with bioluminescence, and the octopus retreats once more into its den. Its arms curl around the entrance like living locks. The shells shift, sealing the doorway. For now, the builder rests, but the structure, like the mind that made it, remains alive, flexible, and ready for change. In a world ruled by impermanence, the octopus has mastered the art of provisional stability. It builds not monuments but strategies, shelters that can be dismantled, moved, and rebuilt as needed. Each den, each collection of shells and sand is an experiment in survival architecture. It is proof that even in the chaotic, predatory marketplace of the ocean, intelligence finds a way to turn vulnerability into strength. The reef may belong to the corals and the fish, but beneath their glittering facades, it is the silent engineer, the octopus, that shows us what it truly means to thrive by design. Down in the twilight fractures of the coral reef, where daylight thins into shimmering bands and the architecture of life folds into tight labyrinths, a shadow waits. Its body sways like smoke between the corals, head emerging just enough for two glassy eyes to monitor the current. The moray eel, long, muscular, and patient, is a creature that has turned the economics of real estate into a fine-tuned art. In this underwater metropolis, where every crevice, crack, and hollow has value, the moray is both landlord and assassin, a silent ruler of the reef's prime hideouts who rents its space not for coin but for survival. The camera drifts close, revealing the eel's head framed by coral outcroppings. Its body undulates slowly, mouth agape in a perpetual rhythmic opening and closing. To an inexperienced observer, this motion looks like menace, a constant threat display. But in truth, it is breathing. Morays have evolved narrow gill openings that require continuous pumping to maintain oxygen flow. Every flex of the jaw is a quiet tax paid to physiology, a reminder that even in stillness, energy bleeds away. Efficiency for the moray begins with minimal motion. The eel's chosen residence is not arbitrary. It is the product of generations of selection for strategic geography, a network of tunnels that open to multiple exits, angled to catch water flow and conceal its body. In a reef where predators and prey alike are crammed into the same dense architecture, owning the right address is everything. The moray spends much of its life in a single location, investing in the stability of its chosen den. It defends this crevice-like property, repelling intruders with sudden bursts of aggression. Octopuses, lobsters, and even other morays are potential squatters, and evicting them requires violent efficiency. The eel's long body can reverse direction in an instant, twisting like a rope to flush out competitors, its sharp, backward-curving teeth ensuring that once it bites, escape is nearly impossible. But even a landlord must manage resources. Hunting from ambush saves energy, yet limits income. prey rarely wanders directly into a den's strike zone. Too much aggression drains reserves, too little leaves the eel hungry. Here, the moray's genius lies in partnership. Across many coral systems, moray eels and groupers form a remarkable cooperative alliance, one of the few documented cases of interspecies hunting coordination among fish. The grouper, a powerful daylight hunter, searches the reef's open corridors for schools of prey. When a fish darts into a hole to escape, the grouper signals to its ally, a moray that lurks nearby. Scientists have observed these signals: a headshake, a body quiver, a flick of the dorsal fin, an unmistakable invitation to work together. The moray responds by slithering into the crevice, flushing the prey into the open. The grouper, waiting at the exit, delivers the finishing strike. Both share in the spoils, often returning to hunt together again. This cooperation transcends species boundaries in a way rare even among vertebrates. It demands not instinctive reaction, but learned behavior, recognition of another predator's intention. Each participant plays to its advantage. The grouper's agility in open water complements the moray's dexterity in tight spaces. The result is a division of labor not unlike a trade deal. Energy invested by one partner yields a shared return. The moray, the ever-cautious landlord, profits from the grouper's mobility, effectively charging a fee in the form of shared prey. In return, the grouper gains access to a service that no brute strength could replicate: the eel's ability to infiltrate the reef's hidden corridors. Such partnerships, though rare, are built on complex evolutionary incentives. For the moray, cooperative hunting amplifies access to food without requiring territory expansion. In the densely populated reef economy, growth often means confrontation, and confrontation invites injury. The eel's skin, lacking scales, tears easily, leaving it vulnerable to infection. Instead of conquering new ground, the moray leverages relationships to extend its reach, gaining benefits without incurring the costs of expansion. This is the biological equivalent of outsourcing labor while maintaining ownership, a landlord who grows richer not by building more property, but by managing it more intelligently. The camera pans deeper into the crevice system. Here, inside the eel's lair, lie the remnants of its meals: crab shells, fish bones, and fragments of coral. This midden is not waste, but record-keeping. Its presence signals long-term occupancy. Cleaner shrimp and wrasses gather at the entrance, attracted by the scent of decay. The moray allows them to enter, even parting its jaws slightly to grant access. This is not benevolence, it is maintenance. In the underwater economy, these cleaners act as contractors, removing parasites, dead tissue, and food residue from the eel's mouth and skin. The relationship reduces infection risk and extends the eel's operational lifespan. In return, the cleaners gain a steady food source, a recurring service contract. The moray's compliance during cleaning, often lasting several minutes, reveals an evolutionary truce built on trust. A single reflexive snap could end the cleaner's life. But over millennia, both parties have learned that cooperation pays better than betrayal. Yet, despite the veneer of calm, the moray's world is one of constant tension between patience and violence. When prey drifts close, a stray reef fish grazing near its den, the eel transforms from a motionless tenant into a coiled spring of predatory muscle. Its body launches forward with astonishing acceleration, propelled by wave-like contractions along its spine. The strike is silent but devastating. Unlike most predators, morays possess a second set of jaws, the pharyngeal jaws, hidden in their throats. When the primary jaws seize prey, the pharyngeal jaws shoot forward to pull the victim deeper, preventing escape. It is an evolutionary innovation unique among fish, a built-in conveyor system that ensures every capture converts into consumption. In economic terms, the moray has achieved near zero loss on successful hunts. Efficiency defines every aspect of its physiology. The moray's long, narrow body allows it to exploit microhabitats that larger predators cannot access. Its sensory systems are tuned to this dim, confined world. Lateral line organs detect pressure waves from distant motion, while chemical sensors in its nostrils trace faint plumes of scent through the maze of coral. Its small eyes are adapted for low light, relying less on color and more on contrast. These senses combine to create a three-dimensional mental map of its territory, every current, every echo memorized and catalogued. The eel knows where water flows fastest, where sand accumulates, where prey hides. Each crevice becomes an extension of its mind, a portfolio of assets managed through constant observation. Still, real estate in the reef is competitive. Young morays, not yet strong enough to defend premium crevices, must settle for marginal properties, open sand flats, unstable rubble, or crevices near predators. Many do not survive long enough to claim a better den. The successful ones are those that master timing and negotiation. Some occupy temporary refuges abandoned by others. Others cohabit, uneasy roommates who share space until one outgrows or outmaneuvers the other. These moments of overlap expose the delicate balance of reef economics. Survival depends not on dominance alone, but on adaptability and timing. The moray's patience, its willingness to wait, to conserve, to strike only when the odds align, is its greatest investment strategy. The partnership with the cleaner fish underscores this theme of maintenance as a form of wealth. Parasite load directly affects an eel's foraging efficiency, growth rate, and even reproductive success. Cleaners, then, are not luxuries. They are essential labor, the unseen custodians of the moray's health economy. Studies have shown that morays actively seek out cleaning stations, even traveling across dangerous open ground to reach them. Upon arrival, they exhibit ritualized submission, body relaxed, mouth wide, signaling peace. The cleaner wrasses approach, pecking delicately at parasites along the skin and gums. This relationship, once considered mere curiosity, now represents one of the most important symbiotic systems in coral ecosystems. Without these maintenance workers, parasite populations would surge, weakening the reef's dominant predators and disrupting the delicate energy flow of the ecosystem. When the sun sets and the reef transforms, the moray's behavior shifts. Nocturnal species emerge from their dens, turning from landlords into prowlers. They glide between coral heads, searching for sleeping fish or crustaceans. Even here in darkness, efficiency governs their movements. A single strike consumes far less energy than prolonged pursuit, and the eel's flexible body slips through spaces that would trap any rigid hunter. Each attack is calculated, not a gamble, but a transaction, executed with evolutionary precision. The moray feeds, returns, and resumes its station within the reef's architecture, the landlord once more secure in its domain. As dawn filters back through the water, the reef awakens. The eel retreats into its crevice, head facing outward, the morning currents bringing the scent of passing life. The coral hums with renewed activity, schools of fish grazing, shrimp scuttling, sea urchins sifting detritus. In the midst of it all, the moray remains still, silent and watchful, the hidden tenant who both shapes and depends upon the coral's complexity. Its existence is a testament to balance, aggression tempered by patience, ownership sustained by cooperation, power stabilized through partnership. Here in the living city of the reef, the moray eel embodies the principle that survival is not conquest alone. It is management of space, of energy, of relationships. Its crevice is more than a shelter. It is a microcosm of the reef's entire economy, where every movement, every alliance, and every breath carries cost and return. And in that endless negotiation, the moray proves that even the most fearsome predator can thrive not by domination, but by mastering the quiet economics of coexistence. The seagrass meadow stretches out in every direction like an emerald city beneath the waves, blades swaying rhythmically in the soft current, each leaf catching. Glimmers of sunlight that sift down from the surface. To the untrained eye, it appears still, peaceful, almost empty. Yet within this calm, a quiet economy unfolds, a marketplace where every centimeter of territory, every minute of energy, and every flick of a tail carries a price. Hidden among the green strands is a creature that has mastered the art of investment and patience, the seahorse. Clinging upright to a blade of grass with its prehensile tail, the male seahorse is an emblem of paradox. Delicate yet armored, fragile yet fiercely territorial. Its body, covered in bony plates rather than soft scales, is a living compromise between protection and flexibility. Those plates form an exoskeleton that resists crushing pressure and deters small predators, but the cost is steep. The seahorse has sacrificed speed for survival. Unlike the streamlined predators that dart through the open water, the seahorse drifts and anchors, conserving every calorie. It moves not by muscular bursts, but by subtle flicks of a tiny dorsal fin, beating faster than the human eye can follow. This is the energy economy of stillness, a life designed for minimal waste in a landscape where opportunity is measured in millimeters and seconds. The camera draws closer, focusing on the intricate textures of its skin. No two seahorses are identical in pattern or hue. Their pigmentation mirrors the seagrass itself, olive-green streaks fading into sandy yellow or speckled brown. This camouflage is more than disguise, it is insurance. In a world of endless mouths, blending in is cheaper than fighting back. The seahorse lacks speed, claws or venom. Its defense is invisibility, and its success depends on how well it can vanish into the background noise of the meadow. Even its slow rocking motion mimics the pulse of seagrass in the current, ensuring that predators, crabs, pipefish or hunting cuttlefish, overlook the motionless form that clings so quietly among the stems. From this vantage, the seagrass meadow reveals its true scale. Beneath the tranquil canopy lies a complex web of trade and negotiation. Tiny shrimp clean detritus from roots. Snails graze algae that compete with the grass. Juvenile fish shelter in the labyrinth, finding safety in the green density. For the seahorse, this habitat is both refuge and battlefield. Space is scarce, and the best anchoring spots, where the grass density offers concealment and nearby currents deliver drifting prey, are high-value territories. Individuals spend days patrolling small patches, defending their blades not with combat but through quiet occupation. To lose a territory means exposure, and in the open water, even a few body lengths from cover can be fatal. The seahorse's peculiar anatomy reflects this commitment to rooted living. Its tail, fully prehensile, functions like a hand, gripping stems with surprising strength despite its delicate form. This adaptation is more than convenience. It saves energy. By anchoring itself rather than swimming constantly, the seahorse reduces the metabolic cost of staying upright in a moving sea. Each curled grip is an act of conservation, preventing the animal from drifting into open currents where hunting would be inefficient and escape nearly impossible. The tail is both tether and safety line, allowing the seahorse to hold position precisely within its chosen feeding zone. The feeding itself is a study in microeconomics. Seahorses do not chase prey, they trade patience for precision. With a head shaped like a horse's and a snout like a straw, they employ suction feeding, the vacuum strategy of the slow. When a copepod or tiny shrimp drifts close, the seahorse flicks its head forward and inhales with a soundless snap, drawing the prey in before the creature even registers danger. It repeats this hundreds, even thousands of times a day. Each meal is minuscule, barely enough to sustain for minutes, yet the steady rhythm of capture and consumption forms a constant income stream in these horses' delicate budget of survival. To miss too many of these opportunities means deficit. To maintain steady feeding within a small territory means security. But perhaps the most astonishing feature of this animal's economy lies not in how it eats, but in how it reproduces. In most of the animal kingdom, it is the female who invests energy into gestation and the male who competes for access. The seahorse inverts this equation completely. Here it is the male who becomes pregnant, an evolutionary strategy so unusual it has no true parallel among vertebrates. When courtship begins, it unfolds not as a battle but as a dance. A mated pair approaches one another with synchronized sways, their tails entwining briefly as they rise and fall with the current. The display is more than affection. It is negotiation. A successful pair may stay bonded for the entire breeding season, returning to each other daily to reaffirm their partnership. This fidelity is not romantic sentiment. it is risk management. In a habitat where mates are few and distances costly, maintaining a reliable partner ensures reproductive efficiency without the energy drain of constant competition. When the moment comes, the female transfers her eggs into the male's brood pouch, a specialized organ on his abdomen that functions as a biological nursery. Inside this chamber, the male fertilizes the eggs and provides them with oxygen, protection, and a carefully controlled saline environment. The pouch regulates ionic balance, gradually matching the salinity of surrounding seawater as the embryos develop, preparing them for the transition from womb to ocean. This physiological precision turns the male into a living incubator, carrying as many as several hundred developing young at once. The process demands significant energy. His own feeding rate often drops as he diverts resources toward the embryos, effectively investing his stored capital into the next generation. The brood pouch, though outwardly simple, represents one of nature's most advanced examples of paternal investment. It performs many of the same functions as a mammalian placenta, supplying nutrients and hormones that regulate growth. Inside, each embryo receives oxygen-rich fluids, its tiny body folded like a miniature adult. When development is complete, the male's contractions release the fully formed young into the water column, each no longer than a grain of rice, but already independent. From that moment, parental care ends. The juveniles disperse, riding currents across the seagrass plains, a scatter investment strategy that maximizes survival odds by spreading risk. Out of hundreds, only a few will survive to adulthood, but those that do will repeat the same cycle of patience, camouflage, and selective partnership that defines the lineage. The seahorse's reproductive strategy carries ecological consequences that ripple through its environment. By localizing breeding to specific stable territories, populations remain tied to healthy seagrass meadows. Degradation of these meadows, from trawling, pollution, or warming seas, cuts directly into reproductive success. Each lost patch of grass means lost habitat, lost mating grounds, and fewer anchors for future generations. In this sense, the seahorse functions as a biological indicator species. Its presence signals ecological wealth, while its absence marks environmental deficit. Its survival depends not on vast oceanic migrations, but on the quiet persistence of these small underwater gardens that stabilize coastlines and filter the water. The camera lingers on a male resting after releasing his young. His sides still pulse with the memory of contraction. Around him, the meadow sways, indifferent to the transaction that just took place. Tiny fry drift upward, vanishing into the haze of sunlit water, each carrying a genetic inheritance of patience and subtlety. The male resumes feeding, gripping a fresh stem, resuming the slow rhythm of suction and swallow. There is no ceremony, no rest. The next breeding cycle will begin soon, and with it another transfer, another investment, another quiet gamble against the unpredictability of the sea. In this world of constant movement and predation, the seahorse has chosen an extraordinary path: to stay still, to hold fast, to invest deeply. Its slow metabolism, anchored existence, and male gestation are all variations of a single evolutionary principle: to convert risk into stability through careful management of energy and time. Each adaptation, from the gripping tail to the brood pouch, serves the same end: to stretch limited resources across an uncertain life. As the camera pulls back, the meadow appears endless again, a living sea of green where small lives trade energy for safety, where patience itself becomes a strategy. Somewhere among those blades, another pair begins their ritual dance, tails intertwining in the drifting light. The ocean's most meticulous investor prepares once more to deposit his future, not in a nest, not in the open water, but in himself. In the silent arithmetic of survival, the seahorse has learned what few others have. In a volatile ocean, the wisest move is not always to move at all. In the shallows of tropical reefs, beneath the glimmering mosaic of sunlight and shadow, lies an ecosystem ruled not by size or stealth, but by speed and precision. Here, in burrows carved into sand and coral rubble, one of the ocean's most extraordinary creatures conducts its violent trade: the mantis shrimp. Small enough to fit in a human hand, Yet powerful enough to crack glass or shatter crab shells, it is nature's most efficient weapons engineer. Each movement it makes is an act of calculated aggression or defense, its survival built on physics, optics, and entrepreneurial cunning. As the camera glides low over the seabed, we see the entrances of their homes, small, circular burrow mouths fringed by carefully arranged pebbles and shell fragments. To the untrained eye, they seem like the casual work of the current, but every stone, every grain of sand is placed with intention. These burrows are the mantis shrimp's fortresses, built and maintained with military precision. They provide shelter from predators, a platform for ambush, and a vault for food reserves. Inside, the shrimp lines the tunnel walls with mucus, compacting the sand for strength, an underwater engineering marvel capable of withstanding both collapsing sediment and invading rivals. Every individual owns its burrow like property and fights to defend it with the ferocity of a landlord guarding its last investment. Two distinct business models dominate this undersea arms race: the smashers and the spearers. Smashers, the brawlers of the crustacean world, wield club-like appendages, enlarged raptorial arms that can accelerate faster than a bullet leaving a handgun. These appendages strike with such force that the water around them briefly vaporizes, forming cavitation bubbles that collapse in microseconds and release shockwaves powerful enough to kill prey, even if the blow itself misses. This physical phenomenon, cavitation, is a double-edged tool: a flash of plasma, a burst of sound, and a shock loan drawn from physics itself. It allows the smasher to open shells, crack exoskeletons, and access meals sealed off from weaker competitors. The impact is so intense that the strike produces both light and heat, temperatures comparable to the surface of the sun, though the effect lasts less than the blink of an eye. No other animal on Earth uses raw physical energy this efficiently. Spearers, by contrast, take a more surgical approach. Their raptorial appendages are barbed, bladed weapons, precision tools designed to impale soft-bodied prey like fish and worms. They wait at the edge of their burrows, perfectly still, body hidden beneath the sand. When an unsuspecting fish glides past, the spearer launches its attack in less than 0.003 of a second, a strike faster than the neural system of the prey can even register movement. What follows is silence. A single fatal puncture, a brief twitch of muscle, and then stillness once more. The spearer retreats, pulling its catch into the safety of its burrow for consumption. In the evolutionary marketplace of the reef, both strategies thrive, one relying on brute force and demolition, the other on stealth and precision. Two distinct business plans born from the same ancestral blueprint. Yet the true genius of the mantis shrimp lies not only in its weapons but in its vision. Its eyes, perched atop mobile stalks, are among the most sophisticated optical instruments in the animal kingdom. Each compound eye is divided into multiple specialized zones, capable of detecting an enormous spectrum of light. Humans perceive 3 primary colors. The mantis shrimp perceives up to 16. It can see ultraviolet, infrared, and polarized light, wavelengths invisible to nearly all other animals. This means it perceives information layered in ways beyond our comprehension. The iridescent reflections on a fish's scales, the angle of polarized sunlight filtering through the water, the faint flicker of movement in the periphery of its hunting grounds. These abilities give it an unparalleled advantage in locating prey, identifying mates, and detecting hidden predators. In the bright chaos of a coral reef where color and motion can deceive, the mantis shrimp sees not beauty, but data. Its eyes are high-performance sensors, premium optical devices that make its strikes almost mathematically precise. Each day in the life of a mantis shrimp is a series of calculated transactions. The smasher, for example, must balance its risk between hunting and defense. Crabs and snails offer high returns in calories, but also require multiple heavy strikes to open, each impact risking damage to the very clubs that make survival possible. Between molts, the exoskeleton hardens into a rigid shell, giving full strength to its blows. But during molting periods, when the old armor is shed and the new one softens, the mantis shrimp becomes vulnerable. These are the high-risk weeks of its life, the equivalent of living without insurance in a world full of predators. To compensate, many individuals acquire shell mortgages, taking over empty snail shells, abandoned burrows, or crevices that they defend aggressively until their new armor solidifies. During this phase, even a normally confident smasher becomes cautious, retreating deeper into its burrow, plugging the entrance with rubble, and avoiding conflict. When the new exoskeleton hardens, the shrimp emerges reborn, refitted, rearmed, and ready to resume its role as a hunter and entrepreneur of the reef. Burrow ownership also shapes the social and economic fabric of mantis shrimp society. Some individuals hold territories for months or even years, improving their homes like real estate investments. They expand tunnels, build multiple exits, and stockpile food reserves. The burrow becomes not only a shelter, but a center of trade and reproduction. Males and females often share a burrow during mating, and some species form long-term pairs that jointly maintain their home. When two smashers of similar size meet, they rarely risk an all-out battle. Instead, they engage in ritualized displays, flaring their appendages, striking the water, or producing rapid sequences of sound pulses through their raptorial arms. These contests resemble economic negotiations more than fights, with each participant measuring the strength and resolve of the other. Only when neither retreats does the violence escalate. The winner claims the property, the loser retreats, often injured, sometimes fatally. In the mantis shrimp's world, even conflict follows the logic of calculated investment, risk only when the potential gain outweighs the cost. As the camera pans across the reef, we see the aftermath of such activity scattered everywhere. Fragments of shells, crushed coral, and the hollowed husks of former prey. These are not random remnants but signs of efficiency. Mantis shrimp occupy a critical niche in reef ecosystems by recycling calcium carbonate materials. Their relentless pounding not only opens prey but contributes to sediment turnover, breaking down larger shells into fine sand that becomes the foundation for new coral growth. In this way, they are both destroyers and creators, violent sculptors in a continuous cycle of deconstruction and renewal. The most astonishing aspect of their strike, however, is not just power but precision. When researchers filmed a smasher in slow motion, they found that even at speeds exceeding 80 kilometers per hour underwater, the mantis shrimp adjusts its trajectory mid-swing, correcting for refraction, current movement, and prey motion. It predicts where the target will be at the moment of impact, an ability that hints at extraordinary neural processing speed. Its brain, though no larger than a grain of rice, handles sensory integration and motor control with the efficiency of a supercomputer. Every strike is a small act of physics and foresight, the kind of control that inspired bioengineers to study mantis shrimp appendages for designs in impact-resistant materials, robotics, and even aerospace armor. At night, when the reef quiets and plankton drift upward in glowing clouds, the mantis shrimp retreats into its burrow, sealing the entrance with sand and shells. Inside, its sensitive eyes detect the faintest bioluminescence leaking through the cracks. It remains alert, antennae quivering, ready to strike even in darkness. In these quiet hours, the mantis shrimp's world contracts to the dimensions of its home, a fortress, a laboratory, a launch pad for daily conquest. Outside, the reef continues its endless trade, predators hunting, prey hiding, corals feeding. But inside the burrow, a single creature waits with patience and calculation, ready to resume its campaign in the morning. When dawn returns, shafts of sunlight once again reach the seabed, illuminating the sandy plains and coral ridges. From the darkness of its burrow, the mantis shrimp emerges. Its eyes pivot independently, scanning for movement, while the armored plates on its body glint faintly in the light. Every strike it will deliver today, every prey it will capture, every rival it will deter, all are steps in the constant balancing act of survival. To observers, it may look like aggression. To nature, it is economics. The mantis shrimp, in its relentless cycle of construction and destruction, is not simply a predator. It is an entrepreneur of the reef, an investor in force, a master of physics, and a living symbol of evolution's capacity to turn energy itself into a weapon. In the quiet spaces between bursts of violence, the ocean's smallest arms dealer keeps its books in order. One strike, one burrow, one perfectly calibrated blow at a time. Beneath the restless surface of the Pacific, where the swaying kelp forests rise like emerald skyscrapers from the rocky floor, the sea otter drifts between sunlight and shadow, a craftsman at work in one of the ocean's most complex economies. The water is cold here, rarely forgiving, never idle. Every movement in this ecosystem, from the turn of a frond to the click of a clamshell, carries an invisible price. The otter knows this better than any creature in the forest. In its world, energy is the only true currency, and survival depends on how well it manages the daily balance sheet of calories spent versus calories earned. Wrapped in the densest fur of any animal on Earth, 1,000,000 hairs packed into every square inch, the otter defies the need for blubber that sustains whales or seals. Its warmth comes not from fat, but from relentless labor, from a metabolism that burns like a furnace to compensate for the heat that cold seawater greedily steals away. To keep that system running, an otter must eat nearly a quarter of its body weight every single day. That means diving again and again into the icy deep, hunting, cracking, scraping, and prying open prey hidden beneath stones or buried in sand. Each dive is a small transaction in the greater market of survival, a calculation of effort, risk, and reward. When the camera descends through the kelp canopy, the otter appears almost weightless, spinning slowly as bubbles trail from its fur. In its forepaws, it clutches a flat, rounded stone, its personal asset, stored in the loose folds of skin beneath its forearm. Few animals, even among primates, show such intimate understanding of tools. This stone is not decoration or novelty. It is the otter's hammer, its key to unlocking the armored vaults of the sea floor, the urchins, abalone, and clams that form the foundation of its diet. And yet each blow costs time and heat. If the shell proves too thick or the yield too meager, the otter loses energy faster than it can earn it back. Over generations, those that choose well, that learn to balance risk and reward, pass on more than genes. They pass on strategy. Every action in the kelp forest ripples outward. The otter's foraging shapes the lives of everything around it. When it hunts urchins, it prunes the sea's gardeners. Left unchecked, urchins graze through kelp like locusts through grass, stripping entire forests until only barren stone remains. But with otters present, the balance holds. The urchins retreat to crevices, nibbling only on fallen fronds instead of living kelp. The great golden stalks thrive once more, anchoring a network of life that stretches from the smallest amphipod to the grey whale. Fish spawn in the shelter of the leaves, crustaceans feed in the shadowed undergrowth. The kelp forests, lush and breathing, transform sunlight into biomass, locking away carbon and sustaining the oxygen balance of the coastal sea. And it all turns on the appetite of the otter, a keystone investor whose feeding habits govern the health of an entire ecosystem. Seen from above, an otter at rest may seem almost lazy, bobbing on the surface with a stone balanced on its chest and a shell cradled between its paws. But beneath that calm exterior, every motion is an economic calculation. The otter's metabolism runs 3 times faster than that of a land mammal of the same size. A missed meal is more than hunger. It is a deficit that can mean death. The act of grooming, which consumes hours of every day, is not vanity. It is maintenance. The otter's fur must remain perfectly clean and filled with air to insulate against the chill. Dirt, oil, or salt crusts reduce its thermal return on investment, allowing cold water to reach the skin and drain away precious heat. So the otter rolls, rubs, and blows air into its coat, trapping warmth the way a banker guards the last reserves of gold. To survive the Pacific, it must keep its accounts balanced not by luck, but by discipline. In the dim forests below, the camera follows a female as she dives through columns of kelp toward the seafloor. Her whiskers twitch, reading faint vibrations as she probes between rocks. With a quick motion, she wedges her stone beneath a shell and pries. The clam resists. Every second underwater carries an opportunity cost. The longer she stays, the colder her blood runs, the less oxygen she has left. Then, with a sharp pop, the shell gives way. She tucks it under one arm and kicks upward, spiraling through curtains of golden kelp until she bursts into sunlight again. The pup on her chest chirps softly. She positions the clam on her stone and brings her forepaws down in a rapid series of strikes, crisp, precise, efficient. A single meal becomes a lesson in applied physics, a conversion of mechanical force into caloric wealth. But this economy is not always stable. When sea otter populations crash, whether from hunting, disease, or displacement, urchin numbers explode. Kelp forests collapse into wastelands of broken spines and bare rock, reducing fish stocks and starving out countless other species. The ecosystem's productivity, its gross domestic product, so to speak, plummets. When otters return, they do more than restore balance. They restart the engine of the coastal biosphere. Within years, kelp grows taller, carbon sequestration rises, and fisheries rebound. The otter, without intent or plan, acts as both predator and policymaker, stabilizing the entire economic network of the sea through simple necessity. Even its reproductive choices carry economic weight. Females time their births to align with peaks in prey availability. A pup's dependency lasts months, a period during which the mother cannot dive deeply or travel far. Her hunting range shrinks, her risk grows, and yet she continues to feed, groom, and defend the pup with near total devotion. Each calorie she earns must stretch across 2 lives, and each dive becomes a calculation in survival, not just of her lineage, but of her ecological role. As the sun lowers toward the horizon, the kelp forest glows with amber light. Schools of fish move in synchronized waves between the columns. In the distance, an otter surfaces, a puff of steam rising from its fur as it exhales. It floats there for a moment, a small body in an immense economy, every ripple of its world tied to the energy flowing through its veins. Its stone clinks softly against a shell, a sound older than human trade, older than any market. The otter strikes again, not with greed, not with waste, but with the understanding that every act of life in this cold ocean has a cost, and every cost must be paid with work. In the grand calculus of the sea otter is not merely a consumer. It is a regulator, an engineer, and an investor in the future of its ecosystem. The kelp forests it guards are not just habitats, they are living factories, converting sunlight into food, structure, and stability. And at the center of it all floats a single mammal, meticulous, tireless, and profoundly intelligent, proving that even in nature, economics is not just about wealth. It is about balance, resilience, and the constant pursuit of survival in a world where every breath must be earned. Far below the surface, in the blue cathedral of the tropics, sunlight filters through the water in liquid ribbons, striking the broad, outstretched wings of a manta ray. The creature drifts with effortless precision, its body gliding in slow undulations as though it were an extension of the current itself. Around it, a living highway of marine life flows. Plankton clouds pulse with unseen rhythm, small reef fish dart in quick flashes, and cleaner wrasses hover at the ready, suspended like surgeons waiting for their next patient. This is no random assembly. It is a marketplace, a hub of trade and negotiation where time, patience, and cleanliness are the currency, and where the manta ray has mastered the economics of maintenance. The manta's world operates on a balance sheet of energy. Every second spent gliding through the open ocean burns calories, each flick of its 2-meter fins pushing thousands of liters of water aside. Yet the return on this expenditure must always exceed the cost, or the animal's entire migratory existence collapses. Unlike whales or large sharks, mantas have no reserve of blubber to fall back on during lean periods. Their wealth is measured in efficiency. The smoother and cleaner their surface, the more hydrodynamic their flight. Every parasite removed, every patch of dead skin polished away by cleaner fish reduces drag, a microscopic adjustment that can save immense amounts of energy over the course of hundreds of kilometers. It is evolution's version of fine-tuning an aircraft's wings for the long haul. The camera descends toward a coral outcrop, where the water thickens with the motion of other fish, surgeonfish, wrasses, and butterfly fish moving in disciplined formation. A shadow passes above them, vast yet graceful, and the water briefly darkens. The manta has arrived. With a slow, deliberate sweep of its fins, it banks toward the cleaning station, the reef's equivalent of a maintenance dock. Small blue and yellow wrasses dart forward immediately, recognizing their client's signal posture. Wings flared, body tilted upward, mouth slightly open. These visual cues are unspoken contracts, an assurance that the large visitor poses no threat, that its intention is trade, not predation. One by one, the wrasses begin their work. They move across the manta's skin in coordinated precision, picking at tiny copepods, algae and parasites that cling to the surface. The manta holds still, hovering motionless despite the steady current. The act may look serene, but the cost is measurable. Each minute spent waiting here is a minute not spent foraging in plankton-rich water. For a species that must consume up to 13% of its body weight in plankton daily, the opportunity cost of idling is high. Yet the manta's patience reveals a deeper logic. Clean skin and reduced drag translate into faster, more efficient feeding later. What it sacrifices in the short term, it earns back manyfold in energy saved on its long migratory routes. In these waters, where coral heads rise like small islands in an otherwise endless blue, cleaning stations form nodal points in the social map of the sea. The same manta may return to the same station for years, waiting its turn like a trader in a queue. There is order even in apparent chaos. Studies show that mantas observe an unspoken etiquette, a hierarchy of size and dominance. Larger individuals glide in first, smaller ones circle in holding patterns until space opens. Aggression is rare. The market thrives on cooperation. Cleaners, for their part, manage risk by rotating between clients to avoid over-harvesting parasites or damaging sensitive tissue. The relationship runs on trust and time-tested protocol, refined through millions of years of coevolution. Each interaction benefits both parties. The manta gains maintenance, and the cleaner gains a steady supply of nutrition. In the ocean's vast economy, this is mutualism at its most elegant. As the wrasses finish their rounds, the manta shifts, rolling slightly as if to present a new surface for inspection. Its motion stirs up a light rain of sand and plankton, scattering through the sunbeams like snow. The camera follows along the line of its back, revealing the intricate skin microstructure. Thousands of tiny dermal denticles that act as drag-reducing armor, channeling water across its surface in smooth laminar flow. The cleanliness of these microstructures is critical. Biofouling from parasites or algae can disrupt the water boundary layer, costing the manta measurable losses in speed and energy efficiency. A single parasite colony, left untreated, can increase frictional resistance enough to alter its swimming performance. What looks like indulgent stillness is in truth routine optimization, the manta's version of preventive maintenance to secure a profitable journey ahead. Once serviced, the manta resumes its flight. Its massive wings carve through the water in silent arcs, propelling it away from the reef and into open blue. At the oceanic scale, it is an investor diversifying its portfolio, transitioning from maintenance to foraging mode. The journey ahead may span hundreds of kilometers, following invisible routes traced by upwellings and thermal gradients. These nutrient-rich zones function like global trade corridors, carrying microscopic plankton toward the surface in abundance. Here, the manta feeds with mechanical precision, its cephalic fins unfurling like twin sails to funnel the plankton-rich water into its cavernous mouth. Each glide is timed to maximize intake while minimizing drag, a rhythm that allows it to filter thousands of liters per hour while expending barely more energy than floating in place. In this feeding ballet, the manta transforms itself into a living filtration engine. Water passes through fine gill rakers that capture plankton and expel the rest. Each gulp of water may yield mere grams of food, but across hours of foraging, the sum becomes substantial. Its wing beats are slow and deliberate, spaced in near-perfect intervals to conserve energy. The manta's flight path often coincides with the rise of plankton blooms, ephemeral bursts of microscopic life driven by ocean currents, sunlight, and temperature shifts. When these blooms appear, it is the manta's version of a bonus season, an unexpected profit in an unpredictable market. The timing of its migrations across tropical basins aligns closely with these seasonal windfalls, demonstrating a kind of evolutionary forecasting refined by instinct and memory. The open ocean provides no boundaries, yet mantas navigate it with uncanny precision. They use the Earth's magnetic field as a compass, reading subtle geomagnetic variations to orient themselves during migrations that can stretch across entire ocean basins. Combined with temperature gradients and current cues, this navigation system allows them to locate historical feeding and cleaning grounds with remarkable accuracy. Like traders who remember profitable ports, they return to the same regions year after year, some even visiting the same cleaning station at the same time of day. But the manta's mastery of movement extends beyond geography. It lies in physics. These animals exploit what marine engineers call dynamic soaring. By gliding down through denser water layers and rising again into lighter ones, they extract kinetic energy from the ocean itself, reducing the metabolic cost of travel. Each movement follows the same hydrodynamic principles that keep gliders airborne in air currents. The result is one of nature's most efficient migration systems, achieved without conscious calculation but refined through millennia of trial and error. The camera follows as a small group of mantas, perhaps 6 in total, converge near a seamount where currents rise in swirling columns. They form a loose aggregation, their enormous silhouettes drifting in and out of the haze. There is no leader, no coordination, yet each one benefits from the presence of others. The turbulence created by their movement stirs plankton into thicker concentrations, allowing them to feed more efficiently. This collective behavior, while not truly social in the mammalian sense, represents another form of cooperation, a shared exploitation of physics and fluid dynamics that turns randomness into advantage. As the light begins to fade, the manta's form becomes little more than a dark shadow beneath the silver shimmer of the surface. Its journey continues through dusk, each movement deliberate, unhurried, and economically sound. In a world that demands constant motion, it has perfected the art of efficient living, a species that survives not through aggression or abundance, but through calculated restraint. It invests its time wisely, balances its energy budget with the precision of an accountant, and uses partnerships to keep its vast machine in working order. Even its patience, waiting in line for tiny fish to do their work, is an evolutionary gamble that pays dividends across the open sea. In the silent ledger of the ocean, the manta ray stands as one of its most refined economists. Its trade routes stretch across continents, its maintenance contracts span species, and its survival depends on an instinctive understanding that in the great exchange of life, time itself has value. To watch a manta glide through clear tropical water is to see a living equation at work, the seamless balance of physics, biology, and trust that allows one of the ocean's largest travelers to endure, not by taking more, but by knowing precisely when to wait, when to move, and when to let the sea carry the cost. As twilight fades into deep blue, the coastal seabed transforms. The day's diurnal fish retreat into crevices, the corals fold their polyps, and a different kind of labor force awakens. The water thickens with motion, antennae waving, claws flexing, and eyes glinting like red embers under the last shafts of light. This is the hour of the lobster, the reef's industrious miners and nocturnal merchants, creatures that work not for hierarchy or spectacle, but for survival through ownership, strategy, and persistence. When night falls, the lobsters emerge from their burrows, clocking in for the graveyard shift in one of the ocean's most structured and surprisingly ordered societies. The camera descends to the sandy bottom, where shadows stretch between scattered rocks and boulders. A spiny lobster, body armored in bronze and crimson, pushes out from a narrow burrow, brushing sediment from its antennae as if clearing dust from a doorway. Around it, other lobsters begin to emerge, each from its own dwelling, each from a plot of seabed it claims through effort and defense. These burrows are more than homes. They are investments. The structure, size, and location of a lobster's den determine its safety, its access to food, and its chances of reproduction. In this benthic economy, property equals power. To secure such real estate, lobsters dig tirelessly, using their claws to shovel sand and rearrange stones into stable fortifications. They line the interior with pebbles, maintaining tunnels that resist collapse. It is laborious work, but in a world of constant predation, having a solid roof means the difference between life and sudden death. At night, the reef becomes a network of paths, invisible trails laid down through scent. Each lobster follows its own chemical map, a personal trade route encoded with the smells of decaying fish, shell fragments, or the musk of competitors. The ocean may look formless, but for lobsters, it is organized into an olfactory grid. Their long antennae, covered in sensitive chemoreceptors, read these cues with astonishing precision, allowing them to navigate the underwater terrain as effectively as a bird follows magnetic fields. Every trail carries history, a record of who passed, when, and why. These scent highways link burrows to feeding grounds and to each other, forming the infrastructure of a decentralized society where information travels through waterborne molecules instead of words. Each night, lobsters leave their dens and walk the same paths, maintaining predictable routines that biologists once mistook for simplicity. But there is strategy in their repetition. Lobsters are methodical, conserving energy by retracing familiar routes where the odds of reward are highest. They are omnivores with opportunistic tastes, scavenging carrion, hunting small fish, or tearing apart clams and sea urchins when their shells can be cracked. The availability of prey dictates which markets they can access, and this in turn depends on the hardness of their own exoskeletons. The lobster's shell is its capital, both armor and tool. A thick, fully calcified shell allows access to tougher prey, like clams or snails, that softer, newly molted individuals cannot exploit. But that capital depreciates over time. As the shell thickens and stiffens, it becomes cumbersome, slowing escape from predators. The lobster must eventually molt, shedding the old armor in a vulnerable metamorphosis that renews strength but leaves it exposed. A costly retooling period in which it cannot work, cannot fight, and must hide. Molting is the single most dangerous event in a lobster's life. When the old exoskeleton splits, the animal must squeeze out backward, dragging its soft body free. For several hours it lies limp, its body swollen with seawater as it expands into the shape that will fit the new shell once it hardens. During this time, even small fish pose mortal danger. Many lobsters retreat deep into their burrows before molting, sealing the entrance with sand and rubble like miners closing a shaft. Those who survive the molt emerge days later, retooled and re-armored, larger, stronger, and ready to reclaim their place in the social hierarchy. The energy cost is immense. Up to 1/3 of a lobster's stored reserves are consumed in the process. Yet the payoff is substantial. New armor, renewed mobility, and an increased claim on territory and mates. Evolution has made molting both a risk and a reinvestment, a biological renovation financed entirely by time and endurance. Beneath the calm of their movements lies a complex structure of dominance and negotiation. Lobsters are not solitary by nature. Their territories overlap and encounters are inevitable. When two meet along a shared feeding path, the first exchange is not violence, but communication. They wave their antennae, flex their claws, and release pheromones through urine jets located near their faces, a chemical announcement of size, sex, and recent victories. These exchanges form the foundation of what scientists call dominance hierarchies, systems that determine who eats first, who mates first, and who gains access to the best shelters. In a sense, these pheromone exchanges are credit checks, rapid evaluations of social standing that prevent unnecessary conflict. If a smaller or weaker lobster detects the scent signature of a dominant one, it retreats immediately, avoiding injury. Fighting is expensive, not only in energy, but in damage to the exoskeleton, which can take months to repair. However, when hierarchies are contested, the reef echoes with sudden violence. Two males circle, antennae locked in a silent duel of intimidation. If neither yields, they charge, grappling, striking with claws, and flipping each other in bursts of brute force. Water churns with sand and bubbles as they wrestle for dominance. The victor claims not just pride but tangible gains, priority feeding rights, mating opportunities, and secure territory. These contests, though brief, reinforce a system that maintains order within the nocturnal population. The hierarchy may seem primitive, but it ensures that only the fittest individuals occupy the best burrows, guaranteeing that each generation's genetic investment remains strong. As the night deepens, the lobster's movements take on a rhythmic pattern. They roam singly for hours, covering large distances with surprising speed. In some species, particularly those living in colder or more seasonal waters, the nightly wanderings culminate in a phenomenon few observers witness: migration. When conditions change, when storms disrupt feeding grounds or temperatures drop, entire populations of lobsters form processions, traveling together in single file lines across the sea floor. These migrations can extend for tens of kilometers, with hundreds of individuals marching like soldiers, each antenna touching the tail of the one ahead. The purpose is not conquest but continuity, a collective journey toward more stable habitats. The Q formation conserves energy and reduces drag, allowing the group to move efficiently against currents. Each lobster contributes to the migration's momentum, guided by instinct, magnetic fields, and the scent of its companions. In this cooperative movement lies one of nature's rare examples of structured, large-scale coordination among invertebrates, an underwater convoy driven by shared necessity rather than leadership. The camera rises slightly to reveal the scale of the scene. Hundreds of lobsters advance over the seafloor, their antennae forming a glimmering lattice that sways with the current. They're not mindless wanderers, but navigators of invisible highways, following cues that remain partly mysterious even to science. Some researchers believe that lobsters possess an internal compass attuned to Earth's magnetic field, enabling them to orient themselves across vast distances with astonishing accuracy. Others suspect chemical navigation, an olfactory breadcrumb trail laid down and reinforced over generations. Whatever the mechanism, the effect is the same: a living supply chain, ensuring that populations remain connected and stable even in the face of environmental change. When dawn approaches, the activity slows. One by one, the lobsters return to their burrows, retreating from the encroaching light. Each burrow becomes once again a sealed vault, its owner tucked safely inside, antennae still quivering at the entrance. The reef resumes its daytime rhythm, the bright chaos of fish schools, the darting of wrasses, the crackling of shrimp. But beneath it all, the infrastructure remains, a subterranean web of tunnels, scent trails, and social contracts maintained by the miners of the night. To an outsider, a lobster may seem primitive, an armored relic from a prehistoric world, but beneath its shell lies a master of organization. Its life is governed by principles that echo human enterprise: property ownership, labor investment, social hierarchy, and cooperative logistics. Its shell is currency, its burrow real estate, and its migrations the arteries of a self-sustaining system. Every decision, from when to molt to whom to challenge, balances risk against return. It is a life not of impulse, but of calculation. As the sun rises higher and the water warms, the reef's surface shimmers again with color. The camera lingers on a single burrow, where the faint outline of a lobster's antennae sways gently in the current. It will remain there for hours, resting, rebuilding energy for the next night's work. For the reef's economy never truly stops, it merely changes shifts. And when darkness falls once more, the miners will emerge again, ready to maintain their territories, follow their scent trails, and continue the unseen labor that keeps the ocean's living city alive. The shoreline breathes in rhythm with the tides, a pulse that dictates life's tempo for millions of creatures that inhabit this narrow frontier between land and sea. As the waves draw back, the seabed emerges, a world of damp sand, scattered shells, and the slow glint of movement beneath the morning light. Out of the foam and shadow crawl the crabs, the scavenger economists of the coast. They arrive not as solitary wanderers, but as an organized workforce operating under the oldest business model in the ocean: recycle everything, waste nothing, and move quickly before the market closes with the returning tide. Viewed from above, the intertidal zone appears chaotic, a field of motion where claws, shells, and antennae scuttle in every direction. But beneath this apparent disorder lies an intricate system of rules, exchanges, and timing, all built around survival in a volatile economy. For the crab, each tide is a trading day. When the water recedes, the exposed reef or mudflat becomes a temporary marketplace, rich with opportunity. Stranded fish, dying algae, and the carcasses of less fortunate species. When the water returns, the market collapses. In these brief hours, the crab must forage, defend, feed, and often fight. Its entire life runs on a clock calibrated not to sunrise or sunset, but to the moon's gravitational pull. The camera pans low to eye level, where a ghost crab darts across wet sand, pausing to inspect a stranded jellyfish. Its stalked eyes swivel independently, scanning for predators above and rivals nearby. Within seconds, it makes a calculation. The jellyfish's soft tissue offers rich protein, but it is also competition magnet. Its scent will draw others. The crab tears off a small piece, tucks it beneath its body, and retreats toward its burrow, leaving just enough behind to avoid sparking conflict. Such efficiency is the essence of crab economics. Take enough to profit, not enough to provoke. Crabs are nature's recyclers, consuming nearly every form of organic waste that reaches their habitat. Their digestive systems can process an extraordinary range of materials: algae, detritus, mollusks, worms, and even wood fragments softened by microbial decay. This dietary flexibility makes them among the most resilient animals on Earth. In periods of abundance, they gorge on protein-rich prey. During scarcity, they shift seamlessly to plant matter or detritus. It is an evolutionary hedge against inflation, an ability to adapt to resource fluctuations in real time. Species that specialize too narrowly collapse when their food sources dwindle, but crabs endure by diversifying their portfolios. They do not just survive the boom and bust cycles of coastal life, they thrive on them. The body of a crab is a masterpiece of specialization and compromise. Its carapace, the rigid armor that shields its body, is both protection and limitation. It allows the crab to withstand crushing pressure, fend off attacks, and anchor itself against waves, but it also dictates how it grows. Unlike mammals or fish, crabs cannot expand gradually. Growth comes in discrete bursts, requiring the crab to molt, shedding its old shell and forming a new one from calcium and chitin. During the brief period between shells, it is exposed, soft and vulnerable. Some species hide in burrows until their armor hardens. Others rely on camouflage, burying themselves in sand. The risk is enormous, but so are the rewards. A successful molt not only adds size and strength, but resets the crab's tools, the claws that define its trade. Crab claws are not symmetrical ornaments, they are asymmetrical instruments of specialization. Many species develop a dominant crusher claw and a smaller cutter claw. The crusher, thick and muscular, breaks shells and crushes bone. The cutter, slender and agile, manipulates food and performs delicate tasks. This duality turns the crab into both a laborer and a craftsman. One limb for brute force, the other for precision. In evolutionary terms, this division of labor maximizes efficiency. The crab can feed on a wider range of prey and respond flexibly to environmental change. Some species even reverse claw dominance after injury, allowing the smaller limb to regenerate into a new crusher. Adaptability, once again, is their most valuable currency. In the underwater world of coral and seagrass, crabs are the brokers of discarded property. When a hermit crab emerges carrying a shell too small for its growing body, it becomes a participant in one of nature's most remarkable markets. Shells are limited commodities, and each hermit must find one that fits perfectly, large enough to allow growth, small enough to maneuver efficiently. The search for an upgrade often leads to negotiation, theft, or what scientists call vacancy chains. In these chains, multiple hermits line up in size order, each waiting to inherit a shell vacated by the one ahead. When the largest finds a new home, the entire line moves forward, each crab stepping into a slightly larger property. This synchronized exchange, observed in both reef and tide pool species, reflects a collective efficiency that rivals human logistics. It is a market with no currency, no contracts, and yet near-perfect supply chain coordination. But not all transactions are peaceful. Opportunism runs deep in crab society. In densely populated feeding grounds, crabs frequently steal food from each other, exploiting their lateral speed and reflexes. Their sideways motion, a biomechanical adaptation of jointed legs and rigid armor, grants unparalleled agility in confined spaces. The crab can accelerate, pivot, and retreat with astonishing speed, minimizing exposure to predators while maximizing its ability to seize resources. A single claw strike can snatch food from another's grasp before it can react. Yet these confrontations rarely escalate into full combat. Energy conservation governs every move. Fighting is costly, especially for animals that must regularly risk molting. More often, the aggressor takes what it can and withdraws, the biological equivalent of a quick market raid rather than a drawn-out war. The intertidal zone itself operates as the great regulator of crab behavior. Each species must synchronize its activity with the rhythms of tide and light. For shore crabs and sand crabs, the low tide is an open market. Hours of feeding, digging, and mating compressed into a narrow window before the waves return. As the water rises, they retreat underground, sealing their burrows with plugs of wet sand that trap moisture and oxygen. Burrow design varies across species and habitats. Some are simple vertical shafts, others elaborate tunnels with side chambers for ventilation or egg storage. In many coastal regions, entire tidal flats are honeycombed with these burrows, unseen beneath the surface but vital to sediment turnover and nutrient cycling. Crabs, by constantly excavating and reworking these structures, aerate the soil and redistribute organic material, a form of ecological engineering that benefits the entire ecosystem. For species living deeper in reefs or mangroves, tides play a different role. Rather than dictating activity cycles, they influence trade routes, pathways between feeding sites, shelters, and mating territories. The current acts as both constraint and opportunity, carrying food particles toward waiting claws or sweeping competitors away. Crabs read these hydrodynamic signals with remarkable precision. Tiny hairs on their legs and antennae detect changes in flow direction, allowing them to time their movements perfectly. They know when to emerge, when to hide, and when to intercept drifting prey, an instinctive understanding of the ocean's fluid economy that ensures they always move with, never against, the market's current. As dawn breaks, the tide returns. The crabs begin their retreat, vanishing into burrows, under rocks, or beneath seaweed mats. The sand smooths over their tracks. The market closes until the next low tide. Beneath the surface, however, their influence persists. The scraps they consumed, the shells they repurposed, the sediments they reworked, all contribute to the invisible flow of nutrients that sustains the coastal ecosystem. In their endless recycling, crabs maintain equilibrium between decay and renewal, predation and preservation. They are not apex predators, nor architects of coral empires, but something subtler, the accountants of the ocean floor, keeping nature's ledgers balanced. Their survival depends not on strength or speed alone, but on versatility, negotiation, and timing. When resources shift, they shift with them. When tides change, they adapt their routines. Each claw, each burrow, each scavenged scrap represents a calculation, a transaction made in the eternal marketplace of life at the edge of the sea. As the camera pulls back, the shoreline glows under the morning sun. Waves roll in, reclaiming the ground that was theirs. Somewhere beneath, thousands of crabs wait in their chambers, patient and calculating, listening for the signal of the next retreating tide. When it comes, the seabed will awaken once more into a frenzy of movement, trade, and survival. In that narrow, shifting boundary where land and sea continually exchange power, the crabs will resume their work, recycling, rebuilding, and balancing the books of the ocean's oldest economy. The ocean at dawn is a vast and shifting field of signals. Waves carry whispers, clicks, and distant bursts of motion that most creatures ignore or cannot decode. But for dolphins, every sound is currency, information to be gathered, traded, and acted upon. Beneath the surface, a pod of bottlenose dolphins glides in formation, their bodies flashing silver in the rising light. They are not just hunters, they are communicators, strategists, and entrepreneurs of survival, running one of the most sophisticated cooperative networks in the natural world. The camera drifts closer as the pod begins its morning patrol. The water is calm, shallow, a coastal zone rich in fish but full of hazards. Fishing nets stretch across the seabed, boats cut through the surface above, and currents shift unpredictably with each tide. The dolphins move with disciplined precision, scanning both prey and risk in the same sweep of their sonar. Each emits bursts of high-frequency clicks that bounce off objects, forming acoustic maps of their surroundings. The resulting soundscape is rich with data, the density of a school of mullet, the outline of a crab trap, even the heartbeats of other dolphins nearby. In this underwater economy, information is everything, and those who can interpret it most efficiently reap the greatest rewards. Within the pod, hierarchy and specialization govern the flow of this information. There are scouts who lead the group towards schools of fish, drivers who herd prey toward shallow waters, and blockers who position themselves to prevent escape. These roles are not rigid but fluid, changing according to the experience, skill, and sometimes the temperament of each individual. A young dolphin may begin as a follower, mimicking the movements of elders, learning the timing of pursuit, and decoding the unspoken cues that direct a hunt. Over time, it gains autonomy, learning to anticipate, to lead, and to innovate. The structure is less command and more consensus, a network of specialists exchanging signals to execute complex strategies that rival the coordinated hunts of wolves or lions. A sudden shift ripples through the group. The scouts have located a school of sardines shimmering in mid-water. The signal passes down the line, a sharp whistle and a body tilt, and the formation tightens. The dolphins begin to circle. One accelerates, swimming just beneath the fish and releasing a torrent of bubbles from its blowhole. The stream rises in a perfect spiral, forming a cylinder of turbulence that traps the sardines inside. This is the bubble net, one of nature's most elegant hunting technologies, used by some dolphin populations across the world. To the untrained eye, it looks like play. To the dolphins, it is innovation. Bubble netting is not instinctual, it is learned behavior passed down through generations. The technique requires cooperation, timing, and an understanding of fluid dynamics that borders on the mathematical. The dolphins use their sonar to monitor the density of the bubble curtain, adjusting it in real time. Once the fish are corralled into a compact mass, the pod charges upward together, mouths open, slicing through the silvery cloud. The efficiency is extraordinary. Each dolphin gains more energy from the coordinated strike than it would from individual foraging. It is a perfect example of biological economics, shared effort for shared gain. The camera follows another pod in a different part of the world, a muddy estuary where the water visibility is almost zero. Here the strategy is different but no less ingenious. These dolphins, operating in shallow coastal zones, employ what scientists call mud ring feeding. A single dolphin swims in a tight circle, beating its tail against the sediment to create a vertical plume of silt. The disturbance forms a solid, rising wall of mud that traps small fish within its ring. When panic sets in, the fish leap clear of the water to escape, directly into the waiting mouths of other dolphins positioned around the perimeter. This behavior, observed in only a few populations, represents another regional patent, an example of local innovation adapted to specific conditions. The same intelligence that designs bubble nets in one ocean engineers mud rings in another, evidence of culture and technology, not instinct alone. Culture, in the scientific sense, is the transmission of learned behavior through teaching and imitation. Among dolphins, this cultural transmission functions as research and development. Individuals invent new techniques, pods refine and adopt them, offspring learn through apprenticeship. A juvenile dolphin spends years shadowing its mother, watching her every motion, mimicking her vocalizations, and experimenting under her supervision. In some cases, mothers will slow their own hunting to demonstrate techniques, intentionally dropping fish or repeating maneuvers to give the calf a chance to observe. This is teaching, an act of cognitive empathy once considered unique to primates. It ensures that the pod's intellectual capital, the knowledge of where, when, and how to hunt, endures through generations. The pod's social structure reinforces this continuity. Dolphins maintain lifelong bonds, organized around kinship and alliances that function like business partnerships. Within these alliances, individuals exchange support during hunts, defense against predators, and assistance in raising young. They recognize each other's unique vocal signatures, names encoded in whistle patterns, and remember them for decades. Such recognition allows pods to split and reunite fluidly, forming temporary coalitions to exploit particular resources. When fish migrate or environmental conditions shift, the pod can reconfigure instantly, merging with other groups or dispersing to new territories. Flexibility is the essence of their success. Like a well-run corporation, the dolphin pod scales up or down depending on market demand. But every innovation comes with risk. The same coastal shallows that provide abundant prey also bring dolphins dangerously close to human activity. Their hunting strategies, honed for natural environments, can backfire in artificial ones. The bubble rings they use to corral fish are easily intercepted by trawler nets. Mud ring hunts near shore can lead them into shrimp traps or propeller zones. Dolphins are among the most common victims of bycatch, the unintentional capture of non-target species in fishing gear. The irony is stark. Their intelligence, social coordination, and attraction to dense fish schools make them particularly vulnerable to human exploitation. From an ecological perspective, they are victims of their own efficiency. To mitigate these risks, dolphins constantly evaluate trade-offs between safety and reward. Offshore hunting, though safer from human interference, offers fewer prey concentrations. Coastal hunting, though lucrative, is perilous. This decision-making process, observed through decades of behavioral studies, mirrors what economists would call risk management. Dolphins weigh probabilities, the likelihood of reward versus danger, based on past experience. When one strategy fails, they switch. Some pods have even been documented trailing fishing boats to feed on discarded catch, exploiting human activity as an extension of their own foraging network. It is opportunism refined by experience, and it blurs the boundary between wild behavior and learned adaptation to human-induced change. The sensory architecture that underpins all this intelligence is extraordinary. Dolphin echolocation is a biological sonar of staggering precision. High-frequency clicks are projected through a fatty organ in the forehead called the melon, which focuses and modulates the sound. The returning echoes are received through the lower jaw, transmitted to the inner ear, and then processed by a large portion of the dolphin's brain dedicated entirely to sound analysis. In effect, dolphins see acoustically, perceiving size, shape, distance, and even internal density of objects around them. They can distinguish between species of fish based on their echo profiles, identify individual pod members by their whistles, and communicate abstract information across hundreds of meters. Theirs is a world of shapes made from sound, an acoustic economy where perception, communication, and cooperation merge seamlessly. At rest, the pod's cohesion is almost hypnotic. Dolphins sleep with half their brains at a time, one hemisphere staying awake to maintain awareness and breathing. Even in slumber, they rotate through positions, ensuring constant vigilance. No individual ever fully disconnects. The pod's collective awareness persists. When predators like sharks approach, the dolphins respond instantly, forming tight defensive circles with calves in the center. Such coordination requires not just instinct, but an enduring mental map of the group: who is where, who is vulnerable, and who is best positioned to counterattack. Their society functions as a self-correcting system, capable of reorganizing under pressure, a living network that never fully powers down. As the camera pans outward, the pod continues its circuit along the coast, moving with rhythmic grace through shafts of sunlight. Each individual contributes to a greater intelligence, a social and ecological computation that has evolved over tens of millions of years. Every whistle, every burst of bubbles, every synchronized strike represents not just survival, but information management, the storage, transmission, and application of knowledge across generations. In their world, data is life. It is measured in frequencies, shared through clicks, and embodied in action. In the grand balance of the ocean, dolphins occupy a unique position. They are predators, yet they are also architects of cooperation, opportunists, yet guardians of their young and teachers of their kind. Their success lies not in brute strength or numbers, but in intellect and collaboration, the twin forces that allow them to outthink the chaos of the sea. As dusk descends and the light fades to blue-gray, the pod moves offshore, their clicks fading into the depths. Above them, the tide turns, the surface glows faintly under the moon. The ocean's endless data stream flows on, and somewhere within it, the dolphins continue their silent conversation, a symphony of intelligence, memory, and strategy, as intricate and enduring as the sea itself. The ocean is never truly still. Beneath the rolling surface, its currents move like vast ledgers of energy, transfers of life and death, profit and loss, all balanced through an invisible system of checks and redistributions. In this great economy of survival, few enforcers are as efficient or as feared as the tiger shark. Broad-headed, slow-eyed, and endlessly cruising through the blue, it is both scavenger and predator, collector and regulator, an apex tax authority, maintaining the balance by claiming its due from the weak, the wasteful, and the unwary. The camera descends through the pelagic haze of a tropical sea, where light fractures into silver shards across the backs of drifting turtles. Below them, a shadow passes, deliberate, unhurried. The tiger shark glides just above the seafloor, its striped flanks fading into the muted sand like the bars of a phantom barcode. Each slow sweep of its tail propels it forward in silence, its mouth slightly open to channel seawater over the gills. The rhythm is mechanical, almost metronomic, a movement perfected by efficiency. For an animal that may travel thousands of kilometers a year, waste is the only sin. Every calorie burned must yield a return. Unlike the lightning-fast pursuits of short-fin makos or great whites, the tiger shark's predation operates on patience. It is an investor, not a gambler. Its body, built for endurance rather than sprinting, allows it to patrol huge ranges with minimal effort. Specialized muscles in the tail and a large oil-rich liver grant near neutral buoyancy, reducing the need for constant swimming to stay afloat. Its metabolism runs cool and steady, burning energy at a rate that would leave faster predators starving. This slow, deliberate cruising makes the tiger shark a perfect opportunist, able to investigate every scent, every ripple, every flash of motion that might signal profit in the form of food. In the open ocean, luck favors those who diversify. The tiger shark's diet reflects one of the broadest portfolios in the marine world. Sea turtles, rays, bony fish, seabirds, carrion, and even garbage that drifts from human shores all enter its accounts. Its jaw structure is uniquely designed for such flexibility. The upper teeth are narrow and serrated, slicing cleanly through flesh, while the lower teeth are shorter and more conical, built for crushing bone and shell. This dual design allows it to consume everything from soft-bodied prey to armored victims like turtles, whose shells it can cleave with astonishing ease. The sound of such an attack, a dull, resonant crack echoing through the water, is the sound of a perfectly executed transaction. High effort, high reward. The tiger shark's role extends far beyond individual hunts. In ecosystems dominated by abundance, it acts as a necessary regulator, removing the diseased, the aged, and the inefficient. Sea turtles weakened by parasites, rays slowed by injury, or fish schools that crowd too densely all draw its attention. By preying upon the compromised, it reduces competition and prevents outbreaks of disease, a biological audit that strengthens the entire community. Ecologists refer to this function as top-down control, but it might better be understood as taxation, the unavoidable price of survival in a system that rewards fitness and punishes excess. In this way, the tiger shark enforces discipline, ensuring that energy circulates efficiently through the reef and beyond. But not all its income comes from active hunting. The tiger shark is an accomplished scavenger, one of the few large predators that can locate and consume carrion across vast distances. Dead whales, floating carcasses, or discarded fish bycatch all trigger the same response: an investigative pass, a testing bite, and then full commitment.
Its sense of smell is legendary. A single drop of blood diluted in millions of liters of seawater can draw its attention from hundreds of meters away.
The sensory organs along its snout, electroreceptors known as the ampullae of Lorenzini, detect faint electric fields emitted by living or recently dead tissue. To the shark, the ocean is alive with signatures, invisible pulses that reveal the presence of opportunity long before it becomes visible. It is this combination of smell and electrosense that allows tiger sharks to function as the ocean's cleanup crew, turning decay into sustenance and recycling energy that would otherwise be lost to the abyss. The camera follows a shark through a reef channel where the water funnels with rising tide. Ahead, a green sea turtle grazes on seagrass near the surface, oblivious to the slow shadow below. The shark adjusts its course, approaching not from behind but from beneath. It ascends gradually, matching the turtle's pace, reading its rhythm. Then, with a burst of power, a single flick of the massive tail, it accelerates, jaws opening in a white arc. The strike is over in seconds. The turtle vanishes in a cloud of bubbles and suspended sand. The shark circles back, collecting the fragments. There is no waste. What it cannot consume will be taken by smaller scavengers later. The reef gains as much as the shark does. Nothing here is lost, only converted. The tiger shark's feeding habits are not random chaos, but part of a larger migratory pattern that follows the cycles of life across entire oceans. In many regions, their movements are timed with precision to coincide with turtle nesting seasons, events that release hundreds of thousands of hatchlings into the sea. For a brief few weeks each year, beaches transform into nurseries and feeding grounds alike. Under the moonlight, the sand ripples with the tiny flippers of hatchlings racing toward the surf, their instincts pulling them into the dark safety of the waves. But safety is an illusion. Waiting just beyond the breakers, tiger sharks patrol in slow arcs, their senses tuned to the vibrations of frantic movement. For the sharks, these hatching events are seasonal windfalls, a biological IPO that floods the market with prey. It is not cruelty, but inevitability, a transfer of energy from one generation to another, maintaining the balance that defines the ocean's rhythm. Yet for all its dominance, the tiger shark's life is defined by restraint. Each meal can sustain it for weeks. Between hunts, it enters long intervals of slow travel, its heartbeat dropping to conserve energy. Researchers tracking their movements have discovered astonishing ranges. Some individuals traveling from tropical shallows to temperate waters thousands of kilometers away, often following subtle thermal gradients or the migratory routes of prey species. These journeys reveal an intelligence that is not conscious in the human sense, but guided by instinct refined over millions of years. The shark reads the ocean like a ledger, temperature, salinity, prey density, and current strength all factored into its movements. It invests in distance when the returns justify the cost. Despite their reputation as solitary hunters, tiger sharks occasionally share feeding grounds with others of their kind. Around whale carcasses or rich turtle aggregation zones, multiple individuals gather, circling with wary patience. There is an order to these interactions, a hierarchy enforced by size and confidence. Dominant sharks feed first, smaller ones wait at the periphery. Conflicts are rare because the stakes, injury or exhaustion, are too high. Instead, they negotiate through posture, proximity, and subtle movements of the pectoral fins. It is a silent diplomacy, proof that even apex predators understand the value of minimizing unnecessary losses. From above, the tiger shark's presence defines the seascape. Its stripes, dark bands along the gray-green back, fade with age, yet they serve a vital purpose in youth. Camouflage among shafts of light filtering through shallow water. Juveniles, less than a meter long, spend their early years in sheltered bays and estuaries, avoiding larger predators, including other sharks. Their diet begins with small crustaceans and fish, expanding as they grow. Each year, their territory widens, their role in the ecosystem deepens. By maturity, they have become fully itinerant, patrolling not a fixed domain but an ocean of opportunity. The tiger shark's reputation as a garbage eater has long colored human perception of it, But that description understates its ecological importance. Its willingness to consume almost anything, living or dead, familiar or foreign, is a form of adaptability that few species can match. In a changing ocean where climate shifts alter prey distributions and currents reshape ecosystems, the tiger shark endures precisely because it is a generalist. It thrives where others falter, capable of shifting from reef predator to pelagic scavenger, from turtle hunter to fish cleaner, without hesitation. It is both the symptom and the solution of ecological imbalance, feeding on the weak when abundance turns to excess, scavenging when scarcity strikes. As the sun sets, the ocean darkens into cobalt blue. The tiger shark continues its slow patrol along the continental shelf, unhurried, unflinching. Schools of jacks part before it. Rays bury themselves in the sand. It does not chase. It waits. Every sense remains attuned to the faint electric signatures of life around it, to the whispers of energy waiting to be claimed. Its eyes, adapted to low light, pick up the glow of bioluminescent plankton swirling in its wake. For a moment, the predator becomes the only moving shadow in a sea of drifting light. Silent, balanced, eternal. In the end, the tiger shark is not a villain nor a mindless killer, but a regulator. It is the ocean's apex accountant, collecting its tax through tooth and patience, ensuring that waste never lingers and weakness never overpopulates. Its presence sustains the order beneath the waves, where life, death, and energy perpetually trade hands. To watch it glide through the blue is to witness the sea's oldest contract in motion, one written not in ink or law, but in hunger, evolution, and the unending arithmetic of survival. The tide is falling, and the shallows awaken. In the thinning water, beams of sunlight ripple across the seafloor, shifting with the current in liquid patterns of gold. The sand looks empty, undisturbed, but it is not. Beneath it, sensors are already reading the faintest electric whispers of buried life. The stingray hovers just above the substrate, wings barely moving, its diamond-shaped body outlined in dusted grains. With a faint shiver, it descends, and the seafloor erupts into motion. A vortex of sand swirls upward, forming a perfect circular crater. When the current settles, a small crab is gone, the stingray's precision engineering complete. To watch a stingray hunt is to see efficiency refined by evolution into an art form. These are not reckless predators, but measured excavators, conducting targeted extractions with tools of extraordinary sensitivity. Their eyes, perched high on the head, are nearly useless for detecting prey beneath the sand. Instead, stingrays rely on a sixth sense, electroreception. Around their snouts, hundreds of tiny gel-filled pores called ampullae of Lorenzini act as biological antennas, detecting the minute electrical signals emitted by muscle contractions in hidden animals. A buried shrimp's twitch or a crab's heartbeat sends an electromagnetic signature through the sediment. The stingray reads it instantly. What to other species would seem a featureless seabed is, to the ray, a map of electrical beacons marking exactly where the next meal lies. The camera shifts closer as the stingray maneuvers into position. It glides a few centimeters above the sand, its pectoral fins undulating with mechanical precision. The wings pulse downward, forcing jets of water through its spiracles, small openings behind the eyes that pump oxygenated water over the gills even when the animal is buried. In a sudden motion, the stingray thrusts its snout into the sand, channeling water beneath its body to fluidize the substrate. The seafloor liquefies, collapsing inward. Within seconds, the prey is exposed. Within seconds, the stingray's mouth, hidden on the underside of its body, acts like a vacuum pump, a piston of muscle generating negative pressure strong enough to suck up the target whole. The result is an almost perfect circle left behind, a feeding crater sometimes called a donut pit. Each of these sand pits represents more than a meal. They are small-scale acts of ecosystem engineering. By disturbing and resuspending the sediment, stingrays increase the oxygenation of the seabed, allowing buried microbes to thrive and recycle nutrients. The disturbed sand also exposes leftover prey fragments, drawing in opportunists, small fish, shrimp, and even juvenile rays that feed on what remains. Over time, entire communities form around these excavations. On busy coastal flats, the marks of hundreds of stingray feedings pockmark the seabed like a lunar landscape, evidence of constant productivity, of energy being redistributed through the food web. Yet from the ray's perspective, these freeloaders are an inevitable cost of doing business. They are the ecosystem's externalities, the unpaid beneficiaries of the stingray's labor. Such behavior reveals a curious paradox. The stingray's efficiency attracts inefficiency. The more pits it digs, the more competitors appear to scavenge the leftovers. Small wrasses hover above the ray as it hunts, darting in to snatch fragments of prey as they escape the sand. Egrets and herons wade nearby in shallow water, watching for the telltale plume that signals an easy catch. Even crabs, relatives of the stingray's usual targets, move in afterward to pick apart the remains. In this sense, the stingray inadvertently subsidizes other species, its specialized hunting method generating a secondary economy of scavengers. The system thrives because the ray is such an effective digger. Every act of consumption becomes an act of production for others. Yet efficiency has limits. Every feeding event carries an energy cost, time spent searching, burrowing, and avoiding predators. The stingray's electrosensory system minimizes those costs by reducing uncertainty. Unlike predators that rely on random search or vision alone, the ray operates almost exclusively on confirmed targets. Studies show that rays often detect prey buried under several centimeters of sediment without making a single false strike. This sensory advantage transforms a chaotic environment into a predictable one, allowing the stingray to maintain a consistent return on energy investment. In economic terms, it is the difference between speculation and precision trading. The stingray's low-profile design complements this strategy. Its flattened body reduces drag and enables stealthy movement over the seafloor. The broad fins not only provide lift but also act as flexible tools for excavation. Some species, like the southern stingray, have been observed modifying their digging technique depending on substrate type, using slow, rhythmic flaps in fine sand, but faster, forceful thrusts in coarse gravel. This adaptability shows a degree of behavioral plasticity uncommon in bottom-feeding fish. The stingray does not simply react to its environment, it modifies it, then adjusts its tactics to the results. But the engineering precision that defines its feeding also exposes it to danger. A buried stingray, hidden beneath sand for rest or ambush, is nearly invisible to passing predators until it moves. When threatened, it relies on one of the most iconic and misunderstood weapons in the sea, the venomous barb. Located near the base of the tail, this serrated spine is sheathed in a thin layer of tissue containing venom glands. It is not a hunting tool, nor a first line of defense. It is an insurance policy, a last resort triggered only under direct threat. The stingray's primary response to danger is flight, not fight. It prefers to flee in explosive bursts, using powerful tail strokes to vanish into deeper water. Only when cornered or stepped on, as happens with humans wading in shallows, does it deploy its weapon. The venom, a complex cocktail of neurotoxins and enzymes, causes intense pain but rarely death. In evolutionary terms, it is deterrence, not destruction. The barb ensures that predators think twice before turning a ray's camouflage against it. The stingray's life follows the pulse of the tides, its movements governed by a schedule older than civilization itself. During low tide, many species retreat into deeper channels, resting in the sand where oxygen levels remain stable. As the water rises, they return to the flats, exploiting the new access to rich feeding grounds. This tidal rhythm acts as a natural production calendar, dictating when and where work can occur. The stingray's hunting efficiency depends on knowing this cycle intimately, not through conscious reasoning, but through the same evolutionary memory that guides migrating birds and spawning fish. Some rays even synchronize with lunar cycles, their activity intensifying during full moons when tides are strongest and prey like worms and crustaceans are stirred from their burrows. The camera glides above a lagoon at night. The water glows faintly with bioluminescent plankton, and the silhouettes of feeding stingrays sweep across the sand like silent shadows. Each descent stirs up a luminous ring of blue light as disturbed plankton ignite in chemical reaction. The effect is breathtaking. The stingray's hunting trails written in living light, transient and vanishing with each movement. Beneath the spectacle lies the same fundamental process, energy transfer. The ray consumes, the scavengers follow, and the ecosystem rebalances. The breeding and life cycles of stingrays add another layer of complexity to their ecological role. Unlike most fish, which reproduce through external fertilization, stingrays are viviparous. The embryos develop inside the mother, nourished first by yolk and later by uterine secretions. This investment means fewer offspring but higher survival rates, another example of efficiency through selectivity. The young, born fully formed, begin hunting within days. From their first dives, they inherit the same tools that define their lineage: electrosense, camouflage, and patience. Some even mimic the digging behavior of adults before they can feed effectively, practicing the motions that will one day sustain them. Despite their adaptability, stingrays face mounting pressures from habitat degradation and human interference. Coastal development alters the tidal flats they depend on. Fishing bycatch removes thousands of individuals each year. Yet even under stress, stingrays continue to perform their invisible labor. Their pits aerate sediments, prevent algal overgrowth, and maintain the health of the benthic community. Remove the stingrays, and the seafloor stagnates, a quiet but measurable loss in the ocean's productivity chain. As dawn returns, the tide shifts once again, the shallows filling with new water. The stingray emerges from the sand and glides away, its form blurring with the seabed until it disappears entirely. Behind it remains a single perfect crater, a signature in the sand. Proof of another successful excavation, another cycle completed. Within minutes, small fish swarm the site, picking through fragments of disturbed sediment. Life continues. In the balance sheet of the ocean, the stingray operates as both engineer and accountant, an architect of opportunity whose actions ripple through entire ecosystems. Each pit is a transaction, energy withdrawn from the substrate, redistributed among scavengers, and reinvested in future cycles of growth. Its electroreception minimizes waste, its venom barb deters risk, its tidal rhythm ensures consistency. There is elegance in such precision, not of artistry but of function, a design perfected by necessity. And as the camera pulls back to reveal the expanse of the coastal flat, pockmarked by hundreds of feeding pits glowing under the angled light of morning, it becomes clear that these quiet engineers shape more than just the sand. They shape the flow of life itself, unseen, methodical, and indispensable. The camera sinks slowly through a haze of green and gold into the twilight of a kelp forest. Giant fronds stretch upward like cathedral columns, their blades swaying in a slow, rhythmic pulse with the surge. Light filters down in broken shafts, illuminating clouds of drifting plankton and the darting silhouettes of fish weaving through the forest canopy. The scene feels timeless, stable, self-sustaining. But at the base of the forest, along the rocks where life begins and ends in cycles of consumption, an army of silent consumers waits. Purple, red, and black spheres cling to the substrate in their thousands, their spines glinting like barbed wire under the filtered light. They move almost imperceptibly, but their impact is anything but slow. These are sea urchins, the unassuming grazers that, under the right conditions, can strip entire marine forests to their bones. To understand the sea urchin is to understand both restraint and collapse. Each individual is an ancient design, a near-perfect sphere encased in a calcified exoskeleton known as a test, covered in hundreds of mobile spines. These spines, moved by small muscle bundles, serve as armor, locomotion, and weaponry all at once. At the microscopic level, each spine's surface is textured with crystalline ridges that resist fracture, a structural engineering feat millions of years in the making. Yet this armor comes at a price. Encased in protection, the urchin sacrifices speed. Its movement is driven instead by hundreds of tube feet, hydraulic appendages extending through tiny pores in the shell. Each one operates via fluid pressure controlled from an internal water vascular system, allowing for remarkable precision but limited pace. The urchin's world is slow, deliberate, and dependent on contact. Its strategy is simple: defend well, eat often, and wait for the world to change in its favor. The mouth of an urchin, hidden on its underside, is a masterpiece of mechanical adaptation. Known as Aristotle's lantern, a name given by ancient philosophers fascinated by its complexity, it consists of 5 interlocking calcium plates that function as chisels. With this tool, the urchin scrapes and grinds its way across rock surfaces, feeding on algae and microbial films. In a balanced ecosystem, this grazing is beneficial. It prevents algae from overgrowing, keeps the substrate clean, and supports coral and kelp regeneration. But in the absence of predators, the same efficiency that maintains order becomes a weapon of overproduction. Left unchecked, sea urchins turn from custodians into conquerors. The camera pans downward through the kelp forest to the sea floor, revealing the aftermath of such imbalance. The once thick canopy thins to ragged strands. The rock is pale, stripped of algae and invertebrates. Urchins swarm the barren substrate like living gravel, their spines clattering faintly against one another in the surge. This is an urchin barren, a marine desert created not by heat or drought, but by relentless consumption. The urchins have eaten their way through the foundation of the ecosystem. The kelp, which depends on a foothold of living algae to anchor its holdfasts, cannot regrow. Without kelp, fish lose habitat, crabs lose cover, and the chain of productivity collapses. It is a perfect ecological market crash, the result of a system stripped of regulation. In a balanced marine economy, predators are the regulators that keep urchin populations in check. In temperate kelp forests, sea otters fill that role with surgical precision. Each adult otter consumes a quarter of its body weight daily, diving repeatedly to pry urchins from the rocks, cracking them open with stones used as tools. A single otter can clear a patch of seafloor of hundreds of urchins in a matter of hours. This predation pressure keeps urchin numbers low and their behavior cautious. Under the watchful eye of predators, urchins remain reclusive, hiding in crevices and feeding only at night. The moment that pressure disappears, through hunting, habitat destruction, or human interference, the urchins emerge en masse. Freed from risk, they expand across the seafloor like an unchecked corporation slashing costs for short-term profit. Their feeding strategy is as brutal as it is efficient. With no living algae left, they begin consuming the very surfaces they inhabit, scraping at detritus, dead kelp holdfasts, even bacterial films. Starvation does not drive them to die, but to endure. Urchins can lower their metabolic rate dramatically, surviving for months, even years, with minimal food. Their ability to persist under famine conditions ensures that recovery of the ecosystem becomes extraordinarily slow. Even after their population crashes, the remaining survivors linger, waiting for the faintest sign of regrowth. The moment kelp spores begin to settle again, the urchins awaken from their metabolic dormancy and consume the new growth before it can mature. It is a feedback loop of suppression, a self-sustaining monopoly that prevents recovery for decades. The physics of the urchin's defense plays a role in its dominance. The spines that cover its body are not only deterrents to predators, but also act as armor priced at the edge of economy. Each spine represents a trade-off. Thicker spines offer greater protection but slow the animal further, while thinner ones increase mobility at the expense of safety. Over evolutionary time, each species has settled on a balance suited to its environment. The purple sea urchin, for example, invests heavily in armor, short, densely packed spines optimized for defense in high predator regions. In contrast, the long-spined urchin of tropical reefs favors agility, with elongated needle-like spines that allow it to wedge into crevices or roll with the current. These design choices, driven by evolutionary market forces, determine how each population responds to predation pressure. Remove the predators, and even the slow, heavily armored species begin to dominate, their high defense costs suddenly becoming irrelevant in a market free of threats. The ecological consequences ripple outward. The loss of kelp forests triggers a cascade that affects not only marine biodiversity, but also carbon cycling and coastal protection. Kelp forests are among the most productive ecosystems on Earth, sequestering vast amounts of carbon and buffering coastlines against storms. Their decline amplifies erosion, releases stored carbon, and disrupts fisheries dependent on the shelter they provide. In the simplest terms, an overabundance of urchins transforms a carbon sink into a carbon source, a reversal of the natural balance that has persisted for millennia. Beyond otters, other predators play regulatory roles in different regions. In tropical waters, triggerfish, wrasses, and spiny lobsters fulfill similar functions, cracking urchins open with teeth, claws, or sheer persistence. In the Caribbean, where overfishing has removed many of these predators, urchin outbreaks have led to widespread reef degradation. Coral structures, once shaded and protected by macroalgae, are left exposed to sedimentation and heat stress. In the North Pacific, historical hunting of sea otters for fur in the 19th century led to the near collapse of kelp forests along entire coastlines. Only with the return of protected otter populations did those systems begin to recover, living proof of how quickly balance can be restored once regulation returns to the market. The urchin's success lies partly in its reproductive strategy. A single female can release millions of eggs in a spawning season, each fertilized externally in the open water. The larvae, called pluteus, drift with the currents for weeks before settling to the seafloor, often far from their origin. This dispersal ensures genetic mixing and rapid colonization, especially in degraded environments where competitors are few. The result is a boom and bust cycle, a biological analog to economic expansion followed by collapse. When conditions are right, abundant food, absence of predators, warm water, the population explodes. When the food runs out, starvation reduces numbers, but not enough to restore equilibrium. The survivors form a standing army, ready to rebuild their empire the moment new resources emerge. There is irony in this efficiency. The same mechanisms that make urchins destructive also make them keystones of recovery when properly controlled. In balanced systems, moderate urchin grazing maintains space for new algal growth, preventing stagnation and promoting species diversity. Without them, kelp forests can become overcrowded, shading themselves and reducing productivity. The problem is not the urchin itself, but the absence of its natural boundaries. In this sense, the animal is both culprit and symptom, a visible measure of how ecosystems respond when their regulators are removed. The camera shifts once more, showing a diver hovering above a barren seafloor. The rocks are coated in a thin film of purple and brown urchins, their spines moving slowly in the surge. The diver's light reveals the faint outlines of kelp holdfasts, ghosts of a vanished forest. But in the distance, something glimmers. A few new fronds rise from a patch of rock cleared by otters returning to the area. Around the regrowth, urchin shells litter the seafloor, empty tests cracked open, their contents long consumed. The forest will return, but only as long as the enforcers remain. In this underwater economy, every species has a role: producer, consumer, recycler, regulator. The sea urchin sits at a pivotal point between growth and collapse, between order and chaos. Its spines, mouth parts, and resilience make it one of evolution's most efficient cost-cutters, a living embodiment of ecological austerity. When predators hold them accountable, they are grazers maintaining balance. When predators vanish, they become monopolists, relentless, uncompromising, and ultimately self-defeating. As the current carries the camera upward, the barren floor fades into the shadows of a recovering kelp canopy. The contrast is stark: the quiet devastation below, the flourishing life above. The lesson is clear. In nature's economy, efficiency without regulation leads not to abundance, but to ruin. The sea urchin does not intend destruction. It simply follows the rules of its design. It eats, it endures, and when unchecked, it consumes everything until there is nothing left to take. The ocean opens in an expanse of turquoise and silver, light playing across the shallows in long, trembling ribbons. Beneath the surface, meadows of seagrass sway like submerged prairies, their blades rising from pale sand and drifting with the tide. Among the slow undulations of these fields, a green sea turtle glides. ancient, deliberate, and unhurried. Each movement of its flippers seems almost meditative, a gesture of balance perfected over millions of years. It is a grazer by design, a herbivore in a world ruled largely by carnivores. But unlike the fleeting grazers of land who must constantly move to evade predators, the turtle's pace is different. It measures its life not in days or seasons, but in decades. Its wealth is longevity, and its success depends on patience. The green sea turtle is a strategist in the economy of time. It matures slowly, sometimes taking 30 years or more before reaching reproductive age. Yet once mature, it can live for over a century, returning generation after generation to the same feeding grounds and nesting beaches. This slow maturation is not a weakness, but an investment strategy, a long-horizon pension plan that pays out in stability rather than speed. The turtle's energy budget, metabolism and growth rates are all tuned to efficiency in a fluctuating environment. While fast-growing fish or invertebrates gamble on quick reproduction and short lives, the turtle's model is conservative, low risk, steady returns, and survival through consistency. The scene shifts to the turtle grazing across a patch of seagrass. It lowers its head and takes a bite, its sharp beak clipping through the blades with surprising precision. What follows looks like routine feeding, but in ecological terms, it is more akin to agriculture. The turtle's repeated grazing stimulates regrowth. Like mowing a lawn, this pruning prevents the grass from becoming overgrown and oxygen deprived. The trimmed shoots regrow faster and richer in nutrients, benefiting not only the turtle, but also the entire seagrass ecosystem. Fish, crustaceans, and mollusks flourish among the rejuvenated blades. Even the microbial life in the sediment thrives as more sunlight reaches the base of the plants. The turtle's feeding creates a cycle of productivity, a renewable system of supply and demand that sustains countless other species. But these underwater pastures are not static. They shift with the seasons, currents, and climate. To exploit them efficiently, green turtles become long-distance commuters. Some populations migrate over 2,000 kilometers between nesting beaches and feeding grounds, a journey across vast open oceans guided by one of nature's most remarkable navigational systems. Embedded in their brains are magnetic sensors that allow them to detect the Earth's magnetic field. Each coastline, each ocean basin carries a distinct magnetic signature, a kind of global fingerprint. The turtle reads this pattern like a map, memorizing the field lines associated with its birthplace. Even after decades and thousands of miles of wandering, it can return with uncanny precision to the same beach where it hatched. This magnetic navigation acts as an evolutionary GPS, a cost-saving adaptation that eliminates trial and error in migration. For a creature expending enormous energy reserves during long oceanic crossings, efficiency is everything. The ability to chart a straight course across featureless seas minimizes energy loss and predation risk. Scientists have confirmed this ability through displacement experiments. Turtles released far from their home waters navigate back with astonishing accuracy, even when deprived of visual cues. The implication is profound. These animals are not drifting with the currents, but actively calculating position through magnetic gradients, perhaps even adjusting course using minute variations in field strength. In the simplest sense, they are living compasses, tuned to a planet-sized instrument. The turtle's journey is not without risk. Juveniles face the gauntlet of oceanic predators, sharks, large fish, and seabirds. The first years of life are spent in what biologists call the lost years, a mysterious phase in which young turtles drift among the open ocean's floating debris and sargassum mats, feeding on small invertebrates until they are large enough to return to coastal shallows. Only a fraction survive this stage, yet those that do emerge transformed. Their shells darken, their diet shifts to seagrass and algae, and they adopt a coastal lifestyle. This transition from carnivore to herbivore is rare among marine reptiles and represents a crucial shift in their ecological role, from consumer of small prey to gardener of ecosystems. As adults, green turtles become keystones of the seagrass meadows. Their selective feeding shapes the structure and productivity of the habitat. By targeting older, tougher blades, they promote the growth of young shoots richer in nitrogen, effectively improving the nutritional quality of their own food source. Over time, these grazed meadows support higher biodiversity, serving as nurseries for countless fish and invertebrates. In this sense, turtles function as ecosystem investors, maintaining the health of their feeding grounds through careful management. Without them, seagrass meadows can become overgrown, smothered by detritus, and prone to collapse. With them, they thrive as stable, self-replenishing systems of life. But the turtle's economic model depends on predictability. And predictability in the ocean is a luxury. Rising temperatures, habitat degradation, and pollution have made seagrass pastures increasingly unstable. Coastal development disrupts the shallow bays where turtles feed. Plastic debris tangles among the grasses they graze. Even climate-induced changes in ocean currents can shift the locations of their feeding grounds, forcing longer and more perilous migrations. In some regions, the decline of seagrass has forced turtles to adapt by grazing on algae-covered reefs, a less efficient diet that provides fewer calories per bite. This adaptation comes at a cost: slower growth and reduced reproductive output, a sign of the tight margins within which these long-lived strategists must operate. The nesting phase of the turtle's life cycle reveals another facet of its long-term investment plan. Females, after years or even decades at sea, return to the very beaches where they once hatched. This fidelity is more than instinct. It is a generational tradition encoded in magnetism and memory. The nesting beach is both birthplace and legacy site, a place where survival is measured not in individuals, but in lineage continuity. Yet fidelity carries risk. Coastal erosion, light pollution, and human activity can transform once suitable beaches into death traps. Artificial lights disorient hatchlings, drawing them away from the sea. Rising sea levels wash away nests before eggs can hatch. In such cases, the turtle's unwavering loyalty to its natal beach, a trait once advantageous, becomes a liability, an evolutionary inertia in a rapidly changing world. Each nesting event is a high-stakes investment. A female may lay over 100 eggs in a single clutch, burying them deep in the sand where temperature determines the sex of the hatchlings. Warmer, sand-producing females, cooler, producing males. This thermosensitive sex determination creates a delicate balance that climate change now threatens to destabilize. In some tropical regions, sand temperatures have risen enough to produce overwhelmingly female populations. For an animal that relies on slow reproduction and long-term stability, such demographic imbalances are catastrophic over time. The turtle's pension plan depends on steady returns across generations, not short-term booms that collapse under environmental stress. The camera lingers on a nesting female under moonlight. Her flippers carve a wide pit, grains of sand cascading in slow motion. The sound is rhythmic, a scraping, sliding whisper against the gentle background of waves. Each egg she lays is encased in a soft, leathery shell, absorbing moisture from the surrounding sand. When she finishes, she covers the nest meticulously, tamping it down with the care of a mason sealing a vault. Then she returns to the sea, her silhouette fading into the surf. The future of her lineage and the resilience of the ecosystem she helped sustain now rest on the survival of her offspring. In the water again, the turtle resumes its steady, methodical life. Its flippers cut through the current with minimal drag, its streamlined shell reducing turbulence to a whisper. Every beat of its heart is calibrated for efficiency. The green coloration of its fat, from which the species gets its name, is not from pigment, but from the chlorophyll-rich seagrass it consumes, a living record of its diet and its place in the food web. Even in death, the turtle's body contributes to the system it maintained, becoming nourishment for scavengers and a return of minerals to the seafloor. The camera pulls back, revealing a mosaic of seagrass meadows stretching to the horizon, punctuated by the slow silhouettes of grazing turtles. The sunlight dances across their shells, turning each one into a mirror reflecting the surface ripples above. In this vast underwater economy, every movement has purpose, every graze has consequence. The turtles' migrations connect continents, their feeding sustains ecosystems, their nesting ensures the continuity of life itself. They are not relics of the past, but enduring symbols of balance, investors in the ocean's long game. If there is a lesson in their existence, it is that endurance is the truest form of intelligence. The green sea turtle survives not by speed or aggression, but by understanding the rhythm of its world. The tides, the fields, the journeys that must always return to their beginnings. It moves through time with patience, turning longevity into profit and transforming the simple act of grazing into an engine of renewal. In a world that values haste, the turtle remains a quiet master of the slow economy. Proof that in nature, the most enduring success belongs to those who know when not to rush. A coral reef at sunrise hums with invisible electricity. The water glows faintly with refracted gold, beams of light bending through rippling surfaces and scattering into rainbows across the corals below. Every crevice teems with motion. Gobies cleaning algae from coral tips, wrasses gliding through shafts of sun, and 1,000 planktonic motes drifting like dust in cathedral air. Near the reef's center, tucked into the folds of a sea anemone, a flash of orange, white and black darts through the tentacles. The clownfish has emerged, cautious but confident, surveying its living fortress. Around it, the tentacles undulate slowly, each tip charged with venom potent enough to paralyze small fish. Yet this little resident moves freely among them, immune to their sting. What looks like an act of defiance is in fact a contractual arrangement, a tenancy as ancient as coral itself. The clownfish and its anemone live in one of nature's most elegant symbioses, a landlord-tenant economy refined through millions of years of negotiation. The anemone provides protection, a home armored with poison inaccessible to most predators. The clownfish pays rent through labor and loyalty. It defends the anemone from intruders like butterfly fish, which would otherwise nibble at its tentacles. It also provides a steady supply of nutrients by bringing in scraps of food, defecating nearby, and fanning oxygen-rich water over its host with constant fin motion. To the casual observer, it seems like a cozy domestic partnership. But beneath the calm choreography lies an economy of survival, a system of exchange where the price of shelter is perpetual service. The camera closes in on the clownfish's body. Its skin glistens, coated in a layer of protective mucus that neutralizes the anemone's stinging cells, known as nematocysts. This chemical disguise must be carefully maintained. Without it, the fish would be electrocuted on contact. Juveniles entering a new host go through a cautious initiation ritual, brushing gently against the tentacles in brief touches until their mucus layer adjusts to match the anemone's chemical signature. This process can take hours, even days, and any misstep means death. Once the bond is established, however, the fish becomes untouchable. Its safety is absolute within the tentacle's reach, a rare luxury in the reef's competitive marketplace. Every day begins with routine maintenance. The clownfish emerges from its shelter and fans the anemone's base, keeping debris from accumulating and preventing suffocation by sediment. It also brings food, small morsels of plankton, crustaceans, or leftover bits scavenged from nearby, feeding itself and, indirectly, its landlord. The anemone's diet benefits from this partnership. Its tentacles absorb dissolved nutrients from the fish's waste, while cleaner water flow helps it respire more efficiently. In this relationship, nothing is wasted. Every flick of a fin, every exhaled bubble contributes to the maintenance of the home. But the reef's housing market is fiercely competitive, and not every clownfish gets an anemone. Suitable hosts are scarce and scattered, and each supports only a single social unit, one dominant pair and a small number of subordinates. The hierarchy is strict, enforced through a size-based social order. The largest fish is the breeding female, the second largest her mate, and the smaller individuals below them non-breeding subordinates. The system functions like a pyramid of opportunity, with each fish's position determined by growth rate. Subordinates must remain small, suppressing their development through stress hormones to avoid challenging the dominant pair. Any attempt to grow too quickly is punished, often with eviction, which in the reef's open water is a near-certain death sentence. This is the clownfish's version of rent control. Stability comes only through submission. Yet this structure is not static. When the dominant female dies, the hierarchy reshuffles. The breeding male undergoes one of the most extraordinary biological transitions in the animal kingdom. It changes sex, becoming the new female. The largest subordinate then matures into the new male. This fluid system, known as sequential hermaphroditism, ensures that no reproductive opportunity is wasted. There is never a vacancy left unfilled, never a gap in the reproductive output of the colony. In evolutionary terms, it is vacancy management perfected, a living example of adaptability as an economic safeguard. This transformation is driven by hormonal control, not genetic limitation. All clownfish begin life as males. Their potential to become female remains dormant until social conditions demand it. The triggers are both chemical and behavioral. The death of the dominant female removes inhibitory pheromones that suppress sex change in the male. Within days, the male's gonads reorganize. Testes are reabsorbed, ovaries develop, and behavioral patterns shift accordingly. By the time the next breeding cycle arrives, the new female is fully functional, ensuring the continuity of the lineage without ever leaving the anemone. The camera pans outward to reveal a wider view of the reef. Nearby, another anemone hosts its own tenant pair, their bright stripes flashing in the current. Each pair occupies a territory roughly 1 meter in diameter, a small parcel of reef real estate, but one fiercely defended. When outsiders approach, the resident male darts forward, spreading its fins and producing bursts of popping sounds through rapid jaw clicks. These acoustic warnings serve as territorial declarations, audible even through the background noise of snapping shrimp and crackling coral. If the intruder persists, the resident attacks, biting, chasing, and driving it away until peace returns. Such defense is vital, for losing the anemone means losing everything: protection, stability, and the right to reproduce. Beyond defense, the clownfish plays an unintentional but vital ecological role as the anemone's caretaker. Its constant movement increases local water flow, enhancing the anemone's gas exchange and waste removal. The fish also protects its host from sedimentation and algal overgrowth by cleaning debris and deterring herbivorous fish. In return, the anemone's stinging tentacles shield the clownfish from virtually all predators except humans. It is a model of reciprocal benefit, a self-sustaining partnership where labor and security exchange hands with mathematical precision. The relationship, however, has boundaries. The anemone is no passive landlord. It regulates occupancy by tolerance, and its stinging cells remain active against outsiders. Only a few species of clownfish are compatible with specific anemone species, each adapted to the host's unique toxin profile. This exclusivity has driven a coevolutionary relationship so tight that both partners' distributions are intertwined. When bleaching events or pollution kill anemones, the fish vanish soon after. When clownfish populations decline, from collection for aquariums or habitat loss, their anemones suffer reduced cleaning and oxygenation, becoming more vulnerable to disease. In this sense, the economic metaphor extends beyond the pair. The loss of one destabilizes the other, collapsing an entire microeconomy of the reef. Beneath the reef's surface dynamics lies a subtler system of resource management: diet. The clownfish's feeding habits are not random, but finely tuned to the health of the anemone. It consumes plankton and algae in moderation, preventing excessive nutrient buildup around its host. Studies have shown that anemones with resident clownfish grow faster and recover from damage more quickly than those without tenants. The reason is twofold. The nutrient cycling provided by the fish enhances the host's photosynthetic symbionts, and the reduced presence of fouling organisms allows more light to reach those symbionts. In effect, the clownfish operates as a maintenance contractor, optimizing its landlord's energy yield in exchange for rent-free lodging. The anemone's protection, meanwhile, functions like an insurance policy. Its venomous tentacles contain capsules of pressurized toxins that fire on contact, injecting neurotoxins capable of paralyzing prey within milliseconds. For most reef inhabitants, this is a death sentence. But for the clownfish, the mucus shield not only prevents harm, but may also carry an anti-predator scent, disguising its presence from potential threats. This chemical cloak makes the fish invisible to many of the reef's ambush predators. It is a perfect example of evolutionary outsourcing. The clownfish doesn't build defenses of its own, but invests in the security infrastructure of another species. As the day fades and light dims across the reef, the clownfish retreat deeper into the anemone's folds. The tentacles contract slightly, curling inward like protective walls around their tenants. Within this fortress, the fish rest, fanning gently to keep water circulating. The reef quiets. Larger predators prowl the open water, but none dare approach the stinging citadel. The partnership, maintained through daily labor and mutual need, endures another night. In the broader economy of the ocean, the clownfish and anemone represent the essence of symbiosis, cooperation born not of altruism, but of calculated necessity. Each partner gains something irreplaceable from the other, and the balance between them is maintained through countless small exchanges of energy, effort, and adaptation. Their relationship mirrors a market in equilibrium, efficient, dynamic, and constantly self-correcting. When morning returns, the cycle begins again. The clownfish emerges, surveys its domain, and resumes its work, chasing off intruders, grooming its host, and maintaining the tiny coral estate it calls home. It will live its entire life within a few square meters, its fortunes tied entirely to the health of its landlord. Yet in that narrow range, it embodies one of the ocean's most sophisticated partnerships. Beneath the bright colors and gentle sway of tentacles lies a living contract, one enforced not by law or logic, but by evolution itself. Here, in this miniature world of risk and reward, the rules are simple but absolute. Protection demands payment. Opportunity requires obedience, and survival belongs to those who understand the cost of living safely in a dangerous sea.